Dr. Roy Polenan, our Honorable Vice Chancellor. Welcome to Bangalore Institute and Professor Dharma. Yeah, why don't you take it? Good to see you here. Yeah, please. Good morning, everybody. All the delegates and dignitaries who are here. Today we have the inaugural program of Global Institute of Academic Network program, GIAN program. This GIAN course number is 2464005 and on advanced alpha and gamma spectrometry for applications in environmental studies. This course is up to the coming Saturday, that is up to December 14th. And for the inaugural program of this GIAN program, we have with us our Honorable Vice Chancellor, Professor P.L. Dharma. And on behalf of CARER and on behalf of all of you, I welcome him for this function. I request our Dean to hand away a floral bouquet to Professor Dharma and welcome him. We have with us the distinguished faculty for this program, Dr. Roy Polenan. He is from Finland. He is the adjunct professor at the physics department of University of Helsinki. He also works in the Radiation and Nuclear Safety Authority, which is famously known as STUK of Finland, as a senior inspector. His main research area is radiation measurement, especially non-destructive alpha spectrometry and gamma spectrometry. That's the reason why we have contacted him to be the faculty for this course. He readily agreed for that. And his other areas of interest are environmental radiation monitoring and in particular air monitoring, atmospheric transport calculations, determination of radioactive particle characteristics, dose calculations, radiation hazard estimations. And he has a specialty in many other areas also. And he has experience of 30 years in this professional field and has published more than 100 scientific research papers. On behalf of Mangalore University, I welcome him to this GIAN program, and at the same time, I would like to thank him for accepting our invitation to be the faculty for this course. On behalf of Mangalore University, I request our Honorable Vice Chancellor to welcome him with a bouquet. Welcome to Mangalore University. Happy to receive you here. This is for you. All beautiful class. Yeah, please be seated. And we have with us the National Coordinator of GIAN program, Professor Anil Agrawal. He has joined us online. Professor Anil Agrawal, thank you for the approving this course, which is very useful, and it is the one and know this GIAN courses in the radiation protection and nuclear measurements is a very rare ones. So we thank you for approving this course, and we welcome you to this program. Mangalore University, our Vice Chancellor is here. Our Vice Chancellor, on behalf of Vice Chancellor, I welcome him. I welcome you for this inaugural program. And we have with us the Dean of Science Faculty, Professor Manjaya. I welcome him on behalf of all of you. And we also have the local coordinator of GIAN program, Professor Ganesh Sanjeev, who is a professor of physics and is also the head of Microtron Center. Probably one of these days, if the time permits, we will visit Microtron Center as well for the so that you can have a view of the linear the cyclic accelerator which is available in our campus. I welcome him also on behalf of CARER and on behalf of all of you. And of course, I would like to mention a few things about this GIAN program. As you know, the CARER is now functioning as a national facility for nuclear radiation measurements. And we have advanced facilities in our center like alpha spectrometer, gamma spectrometer, liquid scintillation spectrometers, calibration facilities. And therefore, what we thought, we are now trying to build up a research team actively working with CARER as the national facility, and the users can come here and use the facilities and for advancing the research in the country. So in that context, with a view to build the capacity of the participants, we have given great emphasis for this program. I welcome all the participants for this GIAN program. You have come from the different parts of the country. Of course, you had long travel, and I hope you had a nice stay yesterday. Thank you for showing the interest and coming all the way from all parts of the country. So I hope you will have a very fruitful day, a fruitful week of learning with the alpha spectrometry and gamma spectrometry. I welcome all of you again, and now I request Dr. Roy Ganesh Sanjeev to speak a few words about this course or the GIAN program.
Good morning, everyone. Honorable Vice Chancellor Professor P.L. Dharma, the National Coordinator Professor Anil Agarwal, the distinguished faculty of this program, Dr. Roy Polanian, Dean of Science and Technology Faculty, Professor Manjaya D.H., my colleague as well as friend and coordinator of this GIAN program, Dr. Karunakar, and all delegates and all the personnel involved in organizing this GIAN program. Very good morning to everyone. Global initiative of academic network. This is the plan, idea of the then MHRD minister, Mrs. Irani. She initiated in the year 2016-17. This is the fourth phase of GIAN program, and 3 phases were conducted by IIT Kharagpur. Now fourth phase is being conducted by IIT Hyderabad. This is the 26th GIAN program which is being held here. I don't know, in the third phase we had submitted 17 proposals from Mangalore University. Maybe because of the changeover of national coordinating institution, or maybe because of due to some other reasons, we could not trace out any one of the 17 proposals. But in the fourth phase, 6 proposals were submitted and 2 are approved and 4 are in pipeline. So this GIAN program, the basic objective of this program is to have some kind of interaction with foreign faculty who is having expertise in a particular area of research, so that the delegates and as well as the course coordinating institute can have a better collaborative, meaningful collaborative ventures to get better results from the research activities. When these 3 programs were conducted, actually being a local coordinator, I had a lot of work, but in the fourth phase, I am thankful to IIT Hyderabad because my job is made very simple, because they are directly contacting with the course coordinator. Otherwise, it would have been a single channel, single approach point. Now I am actually with minimum work regarding this program. But anyway, we are all involved in organizing varieties of programs, GIAN programs on our campus, and I am sure that all the delegates will get benefited out of this program. And please try to see that you exploit all positively all the knowledge and expertise our distinguished subject expert is having. You interact with him, you plan some research collaboration, and may not be individually, maybe through your institution also you can do that. Anyway, the host university, our university, will definitely have some kind of collaborative ventures with Dr. Polanian, who was initially in the University of Helsinki, and now he is taking care of all radiation safety related aspects in Finland. and he will be very useful for all of us to know the things which we have not touched so far. Maybe there may be common areas of research you can explore or extend or extrapolate your research activities through his expertise over here. I welcome all the delegates again on behalf of Mangalore University, and I hope you will enjoy here by attending this program. And I wish everyone all the best. At the same time, Dr. Polanin, who has given his consent to be here, hope he will interact with you and help all of you in case you have any kind of research problems which are unsolved till date. So you can get his contact, and even after this program, you can always talk to him over phone or over emails and get your doubts clear in case you have any, or you can have some mutual discussions on a particular topic so that you can enhance your level of knowledge. I again thank Roy Polanin and welcome all of you for this program, and I wish everyone all the best. Thank you.
May I now request Dr. Roy Polanan to say a few words.
Thank you very much. So, my name is Roy Pöllanen. You can call me Roy. It's a very short name, not very difficult to say. All right. When I yesterday came here in Mangalore, I mean out of the airport, I felt a little bit thermal shock because the temperature was so high, and in Finland just now we have winter, temperatures are minus something. In the southern part of Finland, -5 or something like that. Northern part, -20, -30. So it's a little bit shock. But I think I will survive. Some years ago, Professor Karunakara contacted me and asked that could I present you something about gamma ray spectrometry, alpha spectrometry. I said, yes. All right. Then came corona pandemic. It took almost 4 years, and I practically forget this GIAN program. Last summer, Karunakara contacted me that okay, we got now the resources. I was surprised. Okay, what's this GIAN program? But it was a positive surprise, of course. So I made my presentations in this autumn, and I hope that you like those presentations. They are not very theoretical. They are, in fact, practical and quite simple presentations, but also quite deep in some areas. So it's a pleasure to visit here in your career, and I want to give you a short presentation to ensure smooth cooperation during the course, and please open this and let it circulate. Then another presentation. Finnish people sometimes like strange things, and these are among one of those strange things. These are salted licorice. You can eat this if you like. If you don't like, don't eat. Please circulate it. Okay, once more, thank you, Karunakara, for the invitation, and thank you for participation of this GIAN program. Thanks.
May I now request Professor Anil Agarwal to say a few words about the course and the interaction we had over the last few years. You are muted, Professor Agarwal. No, we are not able to hear you. ಇಲ್ಲಿ ಸರಿ ಉಂಟಲ್ಲ? Hello? No, we are not getting your voice. ನಮ್ಮಲ್ಲಿ ಸರಿ ಉಂಟಲ್ಲ? Yeah. Hello? No. Yeah, we can hear you now.
The dean of the Survey for their help with the process, and of course, the local coordinator, he will, of course, we have tried to revise the process a little bit so that the local coordinator, at least in the post project proposal application process, the local coordinator is not following so much. But of course, there will be more work for the local coordinator and the completion of the course, because at the time we see that have to be submitted and that has to be done through the council and with the help of the local coordinator. But thank you again for all your help, and very, very important. Thank you to Professor Raj for this for taking this time out and bringing us to participate in the GIAN program. This the ultimate objective of the GIAN program is these collaborations between Indian universities and foreign faculty members. Even though the child is primarily from the Indian faculty members side, but I think many times we receive proposals that but in addition to that, the GAP programs obviously don't end with 5 days of individual lectures. The major objective of the GAP program is to develop a lasting collaborative relationship. That relationship could be in the field of pedagogy, the relationship could be in the field of combined research, or writing some kind of monographs together in whichever form or tool that you think could be helpful for the academicians in India. I think that would be very helpful. So my request to the foreign faculty is to see and see how there can be a lasting relationship between Bangalore University and the professor. Just a quick update on the GIAN program that might be of interest to other faculty members who are present there. Under the leadership of IIT Kharagpur, in phases 1 to 3, the GIAN program actually started in 2015, and approximately 1,800 plus courses have been conducted all over India in the first 3 phases. The third phase, which had actually got initiated in 2021-22, that was not really successful for the reason obviously we were hit by COVID and many other things were going on at the same time. And even at IIT Kharagpur, there was a change in the coordinator. Because of certain issues, only a very few handful of courses were approved, and there was no final decision made on certain number of proposals. In 2023 November, we were communicated that IIT Hyderabad will be taking over the charge of this program. 24 onwards, we have been actively monitoring all the progress of these proposals, and all the proposals that were submitted as a part of GIAN Phase 4 were transferred to IIT Hyderabad. Also, we continue to take new proposals at IIT Hyderabad website. So these last 1.5 years has been quite hectic because we had to really literally hit the ground running, because the program was already at full speed when we took over. Already proposals were coming, almost like 10 proposals a day we were receiving at some point. So that was a very large number of proposals that we had to handle. I'm glad to inform you that IIT Hyderabad has very successfully developed a new portal wherein The entire review process is very robust, very transparent, and we have appointed sectional committee chairs who are all luminaries of their respective fields, and each and every proposal is given due consideration, and at least every proposal, almost every proposal, at least has two independent reviewers reviewing the proposal, then a final decision is made by the sectional chair. So the system is very transparent. You can see, in fact, in this particular year, many central universities and NITs are in fact doing better than IITs because of the robust review process. So any institute who is willing to participate more actively is likely to benefit. It is not like IIT Hyderabad being the national coordinating agency. Many of our proposals are getting rejected and we don't have any control over it. As a national coordinating agency, we are dealing that process. We have developed an independent process so that this kind of things does not happen. As far as the phase 4 is concerned, phase 4, we have so far approved almost 200 plus courses in this phase, which are supposed to be conducted. Some of them are being conducted in 24. We are hoping to complete most of them by December 2025, and we are at different stages and different courses. Out of which approximately 100 something courses will be conducted before March. So the Ministry of Education is literally behind us to kind of reignite the GIAN program again, and we would be happy to have any suggestions from the local coordinators and course coordinators on how we can reinvigorate this program, whatever aspects we can add to this program. One particular aspect that I would request the course coordinator, Mr. Karmakar, to consider is that after the course is over, please try to demarcate some time from your calendar and work with your foreign expert and see if you can come up with some kind of a monograph on the subjects that you have taught. It need not be a commercial product, but even if you can come up with some material that can be of public use, please try to see it, make it available for public. Of course, you will be submitting the course for content that will be with the GIAN and we will make it public, but that will be in the classroom lecture notes kind of format. Why don't you also work on a book chapter kind of a thing or a small monograph kind of a thing parallelly, which will be more a reader-friendly material, which could be kind of cited and which could be shown as a product of this GIAN program, which is kind of a secondary benefit of this one. And that will be very helpful actually because there is also a lot of impression, a lot of pressure from the ministry to say that the GIAN program should not end with the 5 days program. Basically, we want to develop a lasting relationship. So there should be some secondary output, tertiary output out of the GIAN program. So with this, I would wish to thank all of you and congratulate you. I wish to thank again and to the foreign expert. I hope he has a good time here during this day. And if there is any question, our office is always open, willing to take questions from you.
Thank you, Professor Agrawal, for your comment. It will be our endeavor to ensure that we come up with a monograph of a book chapter after the completion of the project program. Now I request our Honorable Vice Chancellor to address the gathering.
Do you have also people online?
Yeah.
Participants online?
No participants are online, but only national government.
Okay. Namaste to all. Welcome to Mangalore University once again. Professor Roy, we have the name which is very familiar in Kolkata. Oh, the entire Bengalis are being started with the surname called Roy. So you look more Indian rather than. I'm so happy. Thank you for giving us the license to call you Professor Roy rather than Pulanen. Oh yeah, that's one of the wonderful thing that you said. Thanks also for the great memory, the sweets that you have distributed to our young friends here. What a great gesture.
They are not necessarily sweets.
But the way you gave, even if it is sour, it should be a sweet for them because that's how the gesture was. Professor Anil Agarwal, Professor Manjaya, Professor Sanjeev, and my good friend Professor Karunakar, and all young friends here. A great moment for all of us in Bangalore University to receive Professor Roy, who started saying the moment he landed in India, in airport, it was absolutely a very big surprise because of the temperature. The global initiative of academic network is something which I think we've been, though I'm not a student of science, let me not speak of science, but political science. Something very interesting that is happening around. Earlier, people used to say what brings us together across the world is some of the greatest values. Now, in the absence of the values, it could be democracy, it could be justice, it could be freedom, which is nowhere existing today. Therefore, it never brings us together. But what ought to bring us together is environment. And the only thing that today that can bring people together throughout the world is the environmental concern, which I think is very serious issue today. And every small and big country today, every continents today speak of the environmental issues. At least we speak of the environmental laws in a big way. And we want the parliament to take up very stern action to see that it comes out with a wonderful environmental law so that the next generation lives happily. Now, the initiative for the kind of exercise that you have done today is absolutely welcome gesture. I think Professor Roy is, after reading his, academic achievements, though many of things which I have not understood because it's purely technical, but I thought that Dr. Karunakar and Dr. Ganesh have done a wonderful job, including Dean, in extending invitation to Professor Roy, who is here now with us. And meanwhile, when we were all getting ready for inviting you, Professor Karunakar came and then told me that you are here for almost a week. I suggested him, if only your timetable permits, to meet our other young friends, other than the participants here who have represented different parts of India. That's what I was told. Meet our teachers also here, and students, research scholars, supposing your schedule permits, is to tell how Finland becomes so important today in the globe. And you tell us something about your political experiences to our young friends. Such a wonderful country which I read as political science student. I know Finland geographically where it is, what it is, how it has been a political journey in Finland. But young friends must know why a country like this, though geographically very small, makes a big noise today in terms of advanced research, in terms of political values. And please spare your time to spend some time with our young friends, especially the research scholars here. If you can arrange, that would be a wonderful gesture. You can use our old Senate Hall, Dean Sab and Director. Please see that. Get all the research scholars, give them a chance so that they can listen to Professor Roy. Also, they can see him. As you said, you have promised them that you can have also a global network or collaborative research. They can also think of doing this. But you will all join together to discuss on one issue, that's the environment. So please share your experience of your country with our young friends here. They will be very glad to receive you and then also listen to you. What else I can say instead of talking about the topic that you people are dealing with, where I don't want to commit mistake? I once again welcome you all. Have a wonderful time. Ours is a wonderful campus. Go around, see how beautiful it is in terms of the environment concern that we have. It's absolutely a green campus today. We've been ranked on the top, the first green campus in India today. So just have a look, see how concerned our students are, our faculty are in maintaining the plants and then the trees here. What else I must say? I wish you all the best. If time permits, also see our beaches. May not be as beautiful as the kind of beaches we have in Europe, but also see our places. Wonderful place. I don't know whether you have a slot for them to go out and then see.
Yeah, Saturday afternoon.
Please do that. That would be a wonderful thing. What else I must say? Professor Roy, have a wonderful time. And enjoy our food. We have a very, very different food here. And I'm sure Professor Karnakar will take care of the kind of food that is going to be served with so much of love and then concern. Have a wonderful day.
I would like to thank all those who are here and all those who have made this GIAN program a reality.
Professor Anil's suggestion, I think, is one of the finest things that I heard about for the last few years. Please see these monographs and then some kind of written document is maintained immediately after the program. A wonderful suggestion from Professor Anil. there must be a reason why he has suggested and then stress this. That's it. Okay.
So I would like to thank our Honorable Vice Chancellor for sparing his valuable time, because he has to rush for the syndicate meeting now. But despite that, he was kind enough to give us time and to be here with us. And I thank him on behalf of Carer, on behalf of GIAN network, GIAN program, and on behalf of all of you for being with us today. Thank you, sir. Yeah. I thank Dr. Roy Polanan again for accepting our invitation and coming all the way from, it is almost 24 hours journey from Finland to Mangalore. Yeah. So I thank him again. I thank Professor Ganesh. I thank Professor Manjaya, Dean of Faculty of Science and Technology. And I thank Professor Anil Agarwal for the support he has extended to us all these days. And I thank all the participants, and I thank all the administration faculty, administrative staff, and faculty from sister department for making this GIAN program a reality. Thank you one and all. We now break for a tea for 15 minutes and we assemble here at 10:30. Thank you one and all.
Thank you,
Sir, thank you. Thank you very much. Thank you very much. See you again.
everybody is here. I hope so. So, did you taste this salted licorice? And you are still alive? So it's a more or less Finnish speciality. We like it. I know that other parts of the world don't like it. All right, I will shortly present my, let me say, professional activities in my organization, which is STUK, Radiation and Nuclear Safety Authority. Perhaps I will stay here so that you can see. Is it all right, or so that you can see? Oh, all right. Let's do it this way.
We start?
Yeah,
We start?
yeah, we started now. Is it okay?
Already started.
Yeah.
Because I just wanted to tell you, to begin with, we'll have, would like to hear about about Dr. Rahul Polanin, his research areas, activities, and we'd also like to know about, the STUK, what activities they are doing, so that many of you can, contact him directly and, try to collaborate with him. Yes, please.
Thank you. They are still alive, although they tasted this licorice, salted licorice. So you can see here is Finland, here is India. I came here via Istanbul and then Bombay and Mangalore, and after that it was the thermal shock. Finland is located between Russia, is here, Sweden here. We have 2 reactors in reactor sites in Finland, Olkiluoto area and Loviisa area. There are totally 5 nuclear reactors there. Capital of Finland is Helsinki. Karunakara already presented some of my activities in STUK. I have almost 4 years experience in these areas. I don't read these again. There are some pictures, for example this one, perhaps you know the location of the Chernobyl reactor in Ukraine. I calculated the route of air parcels in the very beginning of the Chernobyl accident. I also analyzed afterwards, of course, some radioactive so-called hot particles from the accident. This is quite small particle size, order of 20 micrometers or something like that. So very small. I have done different research in my organization. For example, I have done skin dose calculations from particles like this, hot particles. I have investigated depleted uranium penetrators. I think you know these penetrators. They are used in Gulf War, for example. I have studied or investigated how UAVs, unmanned aerial vehicles, can be used in environmental monitoring or emergency preparedness. There is a sampler here, and there is a detector inside the fuselage of the UAV, unmanned aerial vehicle. I have made a book of radiation in the environment. Unfortunately, it is in Finnish. And I'm sure that you cannot understand it because Finnish is quite difficult language. Then I have also done different things either Geiger counters or other Finland, and lanthanum bromide scintillation detectors, around 250 pieces of them. The detector population is dense, quite close to the nuclear remote expert support. It's a very, very, how to say, nice center. About the radiation meteorology things, STUC is a national standard laboratory maintaining of national meteorologic standards. However, this laboratory does very much calibration services. Calibrations mean in these cases they are calibrating different kind of equipment. But now my laboratory, measurement and analysis, we are doing mainly measurements and some analysis too. So we do gamma spectrometric analysis from environmental samples, industrial samples, and also direct measurements from peoples. We do complicated analysis too from, for example, from samples from nuclear reactors, primary circuit water. We have only light water reactors in Finland. But we do also analysis from natural isotopes. Then we do radiochemical analysis, uranium, plutonium, americium. This is incorrect, not copper. This should be curium, Cm. Sorry about this. Then we do analysis from strontium, tritium, lead, polonium, radon in water, cross alpha, etc., and also ICBMS measurements. We also made analysis on radon concentration, environmental testing, sampling for control of radioactivity. So we have two counting rooms for gamma ray analysis. This is first one. Second one is here. I will show you very soon a video. Let's see the video first. Most of our detectors, gamma detectors, are more or less same as detectors here. So there are not big differences. However, we have some special ones, like this one. It's a Compton suppression spectrometer. I will explain this in Saturday, I guess so. There is also a alpha beta gamma coincidence system. known as mini panda. There is cosmic ray shielding system known as covered. These are the normal sample or beaker types we are using. I have to say this already now. We are quite often talking about the beakers, why they are so important. Do you have any idea of that? Okay, you can measure by using gamma ray spectrometry any object like this or any object. However, if you want to have quantitative information from this, for example, then you need a well-qualified beakers, which are in this case they are not spherical, they are cylindrical in face, in shape, and if they are cylindrical, these air filters are not cylindrical, but the dirty area is cylindrical. So we can have quantitative results in different cylindrical objects. That's why the vials or beakers are important. And we are using so-called FTRAN software, which is efficiency transfer software. I will explain you this thing later, in later presentations. This is an example how many service-based gamma ray analysis we are doing per year. Mostly we do air filter measurements from construction materials, water samples, ashes, etc., etc. So they are from commercial services. In addition to these, we also analyze several hundred samples from the program of environmental monitoring. And I would like to show you now a video from, can I open it? It should be opened. I tested this yesterday, sorry. Sorry, I will. It should open here. Okay. This is a colleague of mine doing some marks to the samples. So quite high noise. Can you put it off? Yeah, thanks. So the laboratory is more or less same as here, although we have quite a big number of detectors. This is another room. I took this video a few days before I came here to India. Right. Then let's select that one. Okay, this is my colleague. I think you have same instruments here. For example, these Quantulus systems. This is very short video, 1 minute or so. These are some of our alpha spectrometers. She's putting one of the sample in the vacuum chamber of the alpha spectrometer. The detector is there. We have also 2 measurement rooms. All right. Okay, thank you very much. I will go back a little bit. I just put it down. Let's go here. I want to show you one slide. This one. So, why do we have 2 counting rooms for alpha and gamma spectrometry? Do you have any ideas? Any comments?
High active and low active samples.
Sorry?
High active and low active samples.
Well, it could be one possibility, but for example, if I want to measure something, some liquid like this one, and there is a lot of radionuclides inside, I accidentally drop it into the ground. What happens? It will contaminate the room, and it is possible that it is not possible to do any measurement in this room, but we have another room for that. So, because we are responsible, as I meant you, we are responsible of doing measurement during a nuclear incident or accident. That's why it's very essential that we have enough capabilities if something some bad things happen in the lab. So we have separate rooms for counting, so no cross-contamination in the case of an accident in the lab. All the materials, I mean in the concrete and in the floor and ceiling, they are low background materials. We have a separate air ventilation system with quite good filtration for each room. And in the case of a nuclear accident, if there is radioactive material in air outside of our building, then we can use charcoal filters instead of these HEPA filters, so that no radioactive material can come in to the measurement room. However, as you know, charcoal doesn't prohibit noble gases coming into the lab. So we have a possibility to fully stop the air ventilation. And there is also small overpressure compared to the adjacent corridors and rooms. Why this? So if we drop something on the corridor quite close to the measurement lab, so radioactive materials don't go inside the measurement lab. And there is, of course, access control to the measurement labs. So a limited set of people are able to go there. So no contamination goes into the lab. And also we monitor air temperatures, pressure, humidity, and especially radon concentration in the lab. You might know that in Finland we have a radon problem. For example, in my home, radon concentration is 100 becquerels per cubic meter, so it's quite high. And this is because of the uranium and uranium daughters on the soil and ground. All right, this is the presentation of my organization. Do you have any questions, comments, or anything? All right, if so, we can go to the next presentation. I hope that these
Any
two...
questions? Any discussion?
Karunakara, what's the next presentation? Is it?
The radon concentration is interpreted with the result as well.
Pardon?
So whatever the last point,
you
radon
can-
concentration.
Yeah.
So we want to find out the radon concentration. For this
Can you go back to the last?
I will.
last point.
Yeah, just a minute.
Everything point.
Wait a minute.
Last
Let me get go through that.
This is the last, but you mean, you perhaps mean this one.
We are monitoring temperature, pressure, humidity, then radon concentration. So we are telling that we want to monitor the temperature, humidity, pressure, everything, but radon concentration also we want to monitor for the contamination. Radon concentration already from.
It's not possible.
Yeah.
All right.
Any question?
All right. What's the next?
Why you see there is a chair here, there is a chair there?
Is it Karunakara? Is it now? What's the next
Yeah.
one?
First lecture. We go to the first lecture.
Is it nuclear data or is it?
No, it is about. I think it's the radioactivity in the environment.
Okay, there is a. Let's see. It's a. Not this.
Not that. Not that. Let me tell you. Yeah.
I think it's this one. Radionuclides.
Radioactive substances, radiation, and environment.
Yeah. All right. All right. Let's talk about this issue. Please ask me if there are any comments. Okay. So I will shortly give you an introduction, then I will present some sources of radiation and natural radionuclides in the environment, and finally anthropogenic radionuclides. So, as you know, there are radioactive substances and ionizing radiation everywhere in the environment, even in your body. There is, for example, around 1,000 becquerels of potassium 40 around. So, cosmic radiation is coming to the ground, or cosmogenic radionuclides that are generated at high altitudes of the atmosphere. There may be airborne radionuclides in air like radon. And you can inhale that. There is external radiation from radionuclides in living nature. Some industrial activities may release radionuclides into the environment. And especially in the soil, there are a lot of natural radionuclides present there. And of course in your body. There may be, for example, radium-226 or potassium-40 in your bones, in the stomach, and different parts of your body. What is the typical external dose rate in India? I don't know. I know that in Finland it is around 0.2, 0.3 microsieverts per hour.
Or the radiation level?
Yeah, radiation dose rate level.
Yeah. So it is about we get out about.
I think it must be quite close.
Yeah. The
to
annual
that of-
dose is about 2.1 millisievert.
Yeah, annual dose.
Annual dose.
Yeah.
2.1 millisievert in the normal area, but we have places where we have high doses,
Yeah.
like beaches of Kerala,
Yeah.
where there is no monazite deposit,
Yeah. Yes.
where the dose is up to 50 millisievert.
Yeah. All right. And this is also very important. I'm sure that you already know this, but I have to explain this once more. So, radionuclides are transported in the environment as part of the natural cycle of matter, and generally in the same way as stable nuclides. This is more or less general rule, but it's not valid for all radionuclides, but practically most of them. So I know that some of you are doing investigation on transfer factors on radionuclides.
Particularly, we have, of course, we should do that in the beginning. So, shall we, have 5 minutes and we introduce ourselves?
Yeah, it's
tell each of you about, area in which you are working. So that will be, helpful for the expert. For example, because many of you are working on uranium, many of you are working on transfer factors, radioactivity monitoring, or those who are from our BA side, they will be environmental impact assessment, all those things. You can just briefly tell about the current area of research and the institutions you are from. I start with myself. I am Karunakara from Mangalore University. I belong to the Center for Advanced Research in Environmental Radioactivity, and we also have other programs going on. Another center called Center for Applications of Radiation Radioactive Technology and the Medical Physics Department. In this center, we work on monitoring of radioactivity around the nuclear facilities as well as in other natural environments. We work on transfer factors, we work on development of techniques, carbon 14 lithium, and such other things.
My name is Manjunath. I am from Department of.
Please speak loudly.
My name is Manjunath. I am from Karnataka University, Dharwad. My research area is trace elemental analysis.
Sorry, I just intervened. Sorry to stop. Sorry to stop you. Sorry that I stopped you.
Not a problem.
Yeah.
Not a problem.
Yeah.
So my research area is trace elemental analysis in biological and environmental samples using total reflection X-ray fluorescence.
All right.
I am Gopal Krishnan from Indira Gandhi Center for Atomic Research. I am an instrumentation guy working in environmental radiation engineering.
All right.
I am Jordan from Scott Christie College in Nagarkoil. Actually, I am working in coordination compounds and organic synthesis. Now, I have installed somewhat related to this radioactive materials and assessments.
Okay, you are from in another field.
Yeah. Okay. That's the garden is only.
Okay.
Is pushing me to.
What made you to know to attend this course? Because you are from another
One
area.
of my students is doing this assessment.
Okay. Okay.
I'm Rahul Paramesh. I just completed my MSc from this university, MSc Physics. They have a special interest in nuclear physics and astrophysics.
My name is Nancy. I have also completed MSc Physics from Bangalore University this year, and actually my friends suggested me this course, and I felt it interesting.
Myself, Padmanabha. I also the classmates from here only.
Yeah. Please, I hope that because there is a lot of noise there in the corner, so
Padmanabha, and I also mastered done my masters from here, Bangalore University, and I'm really interested in nuclear physics. That's what I need to this.
all right. Thanks.
I'm Aishwarya. I just completed my master's in physics from Kannur University, Kerala, and I just contacted Professor Sir. Just explaining my interest in nuclear physics, and my graduation and master's project mostly dealt with nuclear physics. My graduation was dealt with assessment of lifetime cancer risk in coastal region, and master's project dealt with mass distributions of nuclear system. So I have a profound interest in nuclear physics, so I attended this course.
I'm Dr. Mugaya. I'm a meteorologist in IRE India under the Department of Atomic Energy. Here, process of mineral separation from which is we made rutile, silicon, monoxide, and some other.
I'm Madan K.S. from Man University. I'm a research scholar. I'm doing research field in preparation of polymer gamma radiating material by using polymer compounds.
Myself, Deepika, a research scholar from Bangalore University. Basically, I am particularly radiography. In that, I have measured uranium, radium, radon, and probability numbers.
My name is Sherry from Ramani Institute of Technology from Bangalore, working as a research scholar, and my field is shielding radiation physics by using polymer composites, gamma radiation shielding.
My name is Varsha Roy. I am working in the Defender Technology Development Section in Indira Gandhi Center of Atomic Research under DAE. My field of interest is generally in crystal growth, especially semiconductor compounds like cadmium, zinc, telluride, and piezoelectric compounds. So we work in crystal growth and along with some characterization techniques, and we have some electronics.
I'm Anbasan from Indira Gandhi Center for Atomic Research. I'm working on nuclear engineering.
All right.
Hello, Professor. Hello, everyone. I am Dr. Amit Pandey, and I am working as a scientist B at National Institute of Radiology, Roorkee. And in my study, I am using stabilized scopes of oxygen and hydrogen. Apart from that, tritium and radiocarbon to understand the gamma, the radiation intelligence cycle. And we have also the alpha and gamma spectrometry in our institute. So I am here to know how to use the basic understanding of that.
I'm Ramkop Srimani. I'm from MIT Manipal. So I'm working on organic pollutants. In later stage of my PhD life, I'll be using radiation technology to deal and minimize this organic pollutants. So I really needed an exposure to radiation technologies.
Everyone, I am Sanjay. I am coming from Explore, and I am working in environmental regulatory, mainly in water and soil samples in the mining areas of India, West Bengal. And I would like to learn the HPG more precisely here. That's why I am learning this.
I'm Dr. Manish Chandra, scientist at CWRDM, Calicut. The area of expertise is in environmental monitoring and hydrogeochemistry. And we have a similar setup at CWRDM, so we'll be looking forward to how to use those experiences.
I am Vimala, technical officer CWRDM. I'm actually dealing with some instruments and chromatography, GCMS, alpha spectroscopy system, and HPG like that. So So I want to know how to. I just peripheral knowledge only though. So we have instrument, but I'm not directly dealing with that instrument. But I know instrument. The general instructions I know, but I want to know the more about that alpha spectroscopy, advanced alpha spectroscopy system and its calculation. Similarly, gamma spectroscopy HPG and its calculation of how it is measuring and all that thing. That what I want to learn more. That's why I'm here.
All right.
Hello everyone, myself Trupti Mugli. I'm working as Scientist D in National Institute of Hydrology, Roorkee. My specialization is isotope hydrology. I basically work on stable isotopes. So I am interested more to learn about radioactive isotopes. So I thought this will be a beginning for me with this training. We also have alpha and gamma spectrometry in our institute. So I just joined the new institute and I would like to know how I can utilize that instrument over there. So with the training that I get from here, and also in addition to that, I have specialization in environmental geochemistry. Like I have worked on major ion trace elements in water and sediments, mainly in the Western Ghats River basins I have worked. Thank you.
Hello, sir. I'm Arun. I'm working as chemist in KML. There are dealing with mineral separation and minerals related to titanium, and we come across minerals rich in monocyte. So regarding the measurement of radiation from that mineral, I just want to know more about alpha and gamma spectrometry. So that's why I'm
Hello, sir. My name is GIAN, and I'm from Amrita University, Coimbatore. My final year project was based on heavy mineral analysis and gamma spectrometry on the coastal side of Kollam. So that's why I came here. I wanted to enhance my skills in nuclear.
Good morning, I'm
Morning.
Jesslyn Paul from Kerala. So I work as a geologist at IREL. We are a central government strategic mine. We mine beach and minerals, including monazite. So our unit is planning for a capacity expansion regarding the beneficiation of monazite. Also, so it requires a little more expertise for that. And we also require impact assessment for ISO, which we are certified. And for all those reasons, I'm here to know more about. And we also at present we are only using a preliminary NAI scintillation detector. So we'd like to procure a better detector. That's my
Right.
Good morning to all. I am Nagarajan from IREL India Limited, Manohara Guruchi, under the Department of Atomic Energy. Presently, I am working in IREL Health Systems.
All right.
So myself, already I have some exposure to sodium iodide based gamma spectrometry, where I have been working in internal dose assessment. Now currently we are focusing on measurement of environmental doses from air matrix, especially through gamma spectrometric analysis of HPG using HPG and sodium iodide detectors.
Right.
Myself Sujata, I am working in Indira Gandhi Center for Atomic Research. It comes under Department of Atomic Energy. It's at Kalpakam. The Kalpakam is having a variety of plants, nuclear reactors. So it is a mandatory to assess the environmental on the regular basis. I belong to Environment Assessment Division. So there actually we monitor the air under the normal conditions, also during the accident conditions, stack releases especially. Currently we have two instruments, noble gas monitor to see the FPNG, fission product noble gas monitors. Recently we have procured it, and so this is the stage for me to have exposure to the gamma spectrometry. For that I have.
All right. Thanks.
I am here and my topic is iodine aerosol. We study about how to mitigate iodine in the case of accidental release in the nuclear, if there is a nuclear accident, how to mitigate iodine in the aerosol form, if we can convert iodine to aerosol form, and how we can reduce the iodine exposure in the environment. That is my area.
All right.
Hello everyone, myself Vaishak Sandhu, working as a JRF in the center. My work involves a dietary dose assessment in Kaigan nuclear power plant region.
Right.
Good morning, I am Vijit AP. I am working as a senior research fellow here in Kerala. My working area is on random. So I am
Right.
Hi, my name is Arya. I am working here as Senior Research Fellow, and my area of study is carbon 14, development of carbon 14 techniques in the atomic matrices. Also, I am developing methods for the determination of carbon 14 in bio-based products, and also the determination of carbon 14 in fuel-based products like the sustainable aviation fuel and all these things.
All right.
Thank you very much.
Oh, thank you very much.
Sorry for intervening.
No, it's not a problem. So you have a lot of expertise in different areas. So
Yes.
I hope that these presentations help you a bit. Not necessarily, we do not go very deep in your specific areas, but I hope that you have an impression of the whole entity on gamma and alpha spectrometry. I have to say that in Finland, our culture is, I mean, scientific culture is so that physicists, they do gamma ray spectrometry and chemists do alpha spectrometry. I haven't studied chemist in universities, so it's a little bit problematic for me to understand how to process different things, and I have learned that at least our chemists say that don't let physicists go into the lab. They will, I mean, chemical lab, because it causes troubles. So disaster might follow if you allow physicists to enter in your chemical lab. So that's why I am talking about non-destructive alpha spectrometry in this course, which is quite close to the normal or traditional alpha spectrometry. All right, let's go forward. So, you have to understand that ionizing radiation and radionuclides, they behave in the environmental different. So you have to understand this difference. So radiation is radiation and material is material. And from the perspective of doses to humans, ionizing radiation mostly comes from natural radionuclides in the environment. And this is mostly, this is important thing, because in some specific cases, if you have, for example, cancer and you need some treatment by the aid of not radionuclides, but radiation, then you might have quite big exposures in your body. But normally, the doses comes from environmental radionuclides. So, this is ionizing radiation, and it might happen that radiation from man-made, so-called anthropogenic radionuclides may sometimes have a special role or cosmic radiation, or these human-related activities in hospitals, such as radiation therapy. They may have a special role from the perspective of doses. So, if you have to evaluate radiation exposure caused by the radiation, you have to know characteristics of the radiation and radionuclide location. Is it outside your body or inside your body. So there is external radiation and internal radiation. And if you want to determine activities of the radionuclides, so you have to know characteristics of the radionuclides or the radiation. I have a presentation, I think it's the next presentation on this aspect. Okay, these are the background radiation in the world, in the US or in Japan, and there are also some remarks. I took this from Wikipedia. You can find a lot of information there. For example, this is average annual human exposure to ionizing radiation in millisieverts per year. In the world, total around 3. Karunakara, you mentioned in India 2 point something. 2.1, yeah. In US, it is higher. I don't know why. All right. Karunakara also sorry, already said that there are some highly active areas in India too, in this area. And it is because of the monazite sand and thorum inside the sand. It's more than milligrays per year, and in some locations even 70 milligrays per year. Please look at these publications here. Is it so, Karunakara, that you will send all these presentations to everybody, or?
Yeah.
All right.
Yes.
Nice.
Yeah, we are sending.
Yeah. So, why we are analyze becquerels, not masses? Because radionuclides has mass. But why we are talking about becquerels? So the reason is this. So radioactive substances are the most harmful to the living nature when they decay and emit radiation. So the rate of the decay is better indicator of health effects than the mass. And you can convert the activities here, A, to mass by using this simple equation. So this is molar mass, decay constant, and Avogadro constant. In one of the next presentations, I will show you about LARA application. It is possible to do this more or less automatically. Have you used this LARA application? It's a quite easy application from net. However, in terms of mass, the amount of radionuclides in the environment is often very small. So if we would like to do mass spectrometric analysis from short-lived radionuclides, it's typically not possible. However, it's possible in case of uranium, for example, or thorium, or long-lived radionuclides. So it's easy to detect radiation, quite easy. let's look at the sources of radiation. I mean, natural radionuclides. So, let's start with cosmic radiation and cosmogenic radionuclides. So, most of the cosmic radiation is particle radiation from the sun and space. For example, solar wind and also galactic radiation, but this solar wind is dominating. Solar wind is a plasma. I mean, nuclides without electrons coming from the sun. And it's mainly protons, low energy protons. There are also electrons, and you know this sun's activity period of 11 years. Now, I think that just now the sun's activity is at the highest. Because I know that especially in the northern part of Finland, but also in the South Pole, there are aurora borealis or aurora australis. However, in solar flares, the energy of the protons may be up to 10 giga electron volts. Galactic cosmic rays, they are coming from the Milky Way, supernovas, black holes, neutron stars, etc., etc. It is more or less constant in time. They are composed of atom nuclides, mainly protons and electrons also, of course, but the particle energies, they are very, very high. Very high. But you can see that if a high energy proton, for example, comes to the higher part of the atmosphere, there is an interaction between molecules of air and following a shower of different radiations. It's a so-called secondary radiation. They are primarily electrons, photons, and muons. Muons are because of the decay of pions. They are located here. I don't know, can you see it? Because this is very small, but the pions are generated there. They are quite short-lived elementary particles. And it is the magnetic field of Earth and atmosphere that protects us against cosmic radiation. Same thing is said here. And I already explained this, that secondary radiation and cosmogenic radionuclides, they are produced in the atmosphere. And these particles must be taken into account when you especially use gamma ray spectrometry. Oh, there is a list of some important cosmogenic radionuclides. I mean important from the perspective of radiation measurements by using gamma spectrometry. Tritium, beryllium, carbon-14, aluminum, etc., etc. There are different nuclides. You can see the half-life here. Main decay mode. They are mostly beta emitters, beta minus emitters, emitting sometimes, for example, in the phosphorus case, quite high energy betas, and also some gammas. Which one of you have analyzed these nuclides in gamma ray spectrometry?
In gamma ray, but in liquid synthesis counter, we have
Yeah.
analyzed carbon.
Yeah. All right. Yeah. So you can see here how carbon-14 is produced. And again, you can have more information from Wikipedia, for example. And you have to note that this list is not complete. And these decay energies are only for the highest intensity lines. Then there are so-called primordial radionuclides, which has been forever in Earth. Sorry?
EK mode EC. Electron capture.
Oh, EC, yeah, electron capture. Yeah. It's a decay mode, one of the decay mode. So it's a little bit difficult to see here. Letters are so small. All right. So Earth was formed, or assumed to be formed, from the solar nebula particles by gravitational collapse. And this nebula contained gas, ice, dust, including primordial radionuclides, like these ones. Note that in this list there is no uranium or thorium. I will explain later these things. So the point is that because of the long half-life, these primordial radionuclides have survived up to now, up to present day. This is an essential part of or contribution of the Earth's magnetic field and volcanoes, for example, because there is a huge amount of these radionuclides in the Earth core, and they produce heat when they decay. So you can see here some information about the major heat-producing isotopes deep into the core. In this picture, there is a heat flow in terms of terawatts, and this is time here. Let's go to these decay series. I'm sure that you know this series: uranium decay series, thorium decay series, and actinium decay series. I prepared this, let's put it this way. I'm sure that you have seen these kind of decay series in different formats. I put it in this format, showing that most of the radionuclides are, of course, in the soil, in the rocks, in the ground. And there is radon quite close to the surface of, okay, radon is of course deep into the ground too, but it escapes to air, leading to the fact that these radionuclides are present in air. And there are a lot of radionuclides. When you do analysis, you have to remind that nuclides in the series behave different. This is very, very essential things. And when you do the analysis in gamma or alpha spectrometry, you have to understand this. We will talk these things later. You can see, or perhaps you can see, let's see. So the letters are so small, okay. You can see uranium series, uranium-238 decay series, nuclides, half-lives, decay modes, alpha energies, beta energies, and gamma ray energies and yields. Let's look at the thorium decay series, same thing here. So this is a primordial nuclide, this one, as uraniums are. This is uranium-235. So this list is not complete. There is a lot of other radiations too. But I selected only the most intensity ones. So, as alpha and gamma spectrometry are the main analysis method, but for example, mass spectrometry, there are different mass spectrometers. They are important for analyzing long-lived radionuclides. And this is, as I told you, this is very, very essential. You have to understand when there is equilibrium or not. Because nuclides in the series may behave differently in the environment. And most of the nuclides in the decay series, they are metals. But there are some important exceptions, like radon, which is a noble gas. Have you used this decay calculator? No, it's quite useful for this natural decay series. I suggest you should use that kind of site, because it's as it was said here, it's a universal decay calculator. But you can also find several decay calculators from the net, which are not so well. Some of them are good, some of them are not good. Have you used this one, or?
I have used RAD Pro.
RAD Pro, okay, yeah.
That is good.
Yeah, it's quite simple. Yeah.
Yeah.
But try to use this if you like. Okay, let's look at anthropogenic radionuclides. So, main or most relevant sources are nuclear reactors. I hope that we don't have in the future any nuclear explosions, but there are also radioisotopes produced in industry, hospitals, or research activities. And in case of nuclear reactors, artificial radionuclides can be divided into activation products, which are these one, fission products in the next slide, and transuranics or actinides. What about this cesium-134? It's not a fission product. It's an activation product, in fact. And the reason is that there is a cesium-133 in nuclear fuel, especially when the burn-up is high. And it's generated by the neutron activation of cesium-133. So this is quite common error in understanding what's this cesium. So it's an activation product. So there are a lot of other activation products in the reactors. For example, nitrogen-16 produced by neutron activation of oxygen. Tritium. Which of you are analyzing tritium? Tritium, yeah? You are analyzing, okay. And carbon-14, you are analyzing that, yeah? Generated like this one. So nitrogen-16, it emits high energy gammas, and these two can be analyzed by beta spectrometry. In this course, we are not dealing very much on beta spectrometry because we are concentrated mainly on alpha and gamma. But the methods are more or less same. However, some activation products are generated outside nuclear fuel. I mean, in the tubes, for example, in the primary circuits. These are the activation products. Have you seen these activation products in your studies ever? You have seen? All right. You have? Yeah, all right. Then, about the actinides or transuranics in nuclear reactors. So, these are produced due to the successive neutron captures following alpha or beta decays or other decay types. Perhaps this is the most relevant, and the production looks like this. You have to remember that, for example, in the case of light water reactors, notable part of the fission energy comes from these radionuclides, especially when the fuel burn up is high. And most of these transuranics, they can be determined by alpha spectrometry, except plutonium-241. It's a beta emitting nuclide. Yeah. You have analyzed this, I guess so. Have you? Yeah. All right. So this is a list of actinides and radiation characteristics. You have to remember that this list is far from complete. Where is plutonium? Okay, you can see this plutonium-241. 14 years. All right. So, main radionuclides in the reactors are, of course, they are fission products. And they are, you know this. Okay, there are different types of reactors. In Finland, we have only light water reactors. And the energy is mainly coming from uranium-235 fission. So how many reactor types are here in Finland? I think, do you have fast breeders here?
Yes.
You have? All right. All right. You know these things. I will not go through any more things.
I think,
Hmm?
most of the others might not know about the YUM curve.
Sorry,
They might be knowing about YUM curve. This YUM curve, some of the participants might not be knowing about this GIAN program.
All right. So you suggest I will explain more this point.
Just an introduction.
All right. Let's do that. So, as you know, uranium likes neutrons. If a neutron comes together with uranium-235, fission happens, the nuclides disintegrate mainly in 2 parts, sometimes 3 parts. And for example, if it divides into 2 parts, so the mass number might be 100, and the other part is 140 around. And it depends on the how this distribution is generated. Is it question of high energy neutrons or low energy neutrons? Fission comes mainly in light water reactors from thermal neutrons. Unfortunately, just now, I think that I don't have enough time to explain everything in this issue, but you can read this from the net, for example, or books. But the point is that a lot of radionuclides are produced in nuclear reactors. And this is the biggest danger if you want to look at dangers of radiation. So this is why, for example, my organization is just now present in Finland. So we are monitoring, we are watching that reactors are used safely. And there are no releases into the environment. All right, let's go to this part. Okay, I will show one thing, okay? Let's see. So, in the case of fissionable nuclides like this uranium-235, there is more neutrons compared to fission product nuclei, which means that they are mostly beta emitting nuclides because of the neutron excess in the fission product nuclei. I will show you this. You have probably seen this kind of map. So if a heavy nuclide like uranium disintegrates by fission, it happens so that the daughter nuclides, they are in this area or in this area here, and they are going to that way. So first of main part of these nuclides here in the lower part of this map, they are very rapidly decaying to stable nuclides, which are usually marked as black boxes there. Now, okay, for example, this chain of fission products, it is present here. You can look this afterwards. It's very important to understand this. Okay, I hope that you will later look at these kind of maps. It's very useful in general. Of course, if you are doing your practical job, it's not very often I do not very often look at these maps, but sometimes I have to watch that if I detect some strange radionuclides, I have to check the nuclide map and see what's the origin of that nuclide. All right. So, from the point of view of the fission product release in the environment, especially in nuclear accidents, they are often classified as groups based on their amount of fuel, their chemical form, half-life, volatility, behavior in the environment, or the risk of producing high radiation doses. All right. I cannot go deep into this area because this is a very this is an area which is used, for example, if you want to do risk analysis of nuclear reactors and the consequences that they cause to the people. So you have to understand also these things. All right. There are some important fission products in this slide that might release in a severe nuclear reactor accident. As you can see, they are grouped in different groups. Iodine group. There are some short-lived nuclides. Maybe iodine 131 is the most important. Which one of you have analyzed iodine? You have. Okay. There is cesium group, tellurium group, ruthenium group, lanthanum group, cerium group. And as you see, these groups are classified according to these things, not because of the half-life, but because of the volatility. This is perhaps the most important thing. Of course, amount in the nuclear fuel too. All right. Let's look at the radionuclides from nuclear detonations. And nuclide distribution, it depends on the type of the bomb. Fission or fusion bomb. There are, of course, other types of bombs too. And also structural materials of the bomb. These materials are activated by neutron activation. As said here, you have to remind that ground material, soils, can be activated too in case of low altitude detonation. I think that you already know that, for example, atmospheric nuclear tests, they are forbidden. I'm not sure about this word forbidden, but most countries obey this rule. However, there are some countries, for example, North Korea. Fortunately, they haven't exploded this in the atmosphere. They have done underground tests. Also, France has done in Mururoa area some nuclear tests. Fortunately, in this case, noble gases are the only relevant radionuclides, and they are not generally very dangerous in terms of doses to humans. Because if you inhale them, they don't stay in your body, they will go out in the same way. All right. In the previous, I said in the previous slide that there is a Nordic project known as TEMEDET project. They made calculations on radionuclide inventories in the case of nuclear explosion, and this is the list of their calculations. They calculated a list of radionuclides according to the time from the detonation, 30 days, 100 days. And as far as I understand, they are in the order of activities. Higher activities are here in the top of the list, lower activities in the bottom of the list. And again, large number of data can be found from the net. All right. Do you know CTBT agreement? So most countries obey this agreement, which denies to do atmospheric nuclear test. There is a separate organization in Vienna that make monitoring of radionuclides, not only by detecting radionuclides, but they are using also monitors that are used in earthquakes, infrared sounds, but they are also using Nobel case monitors. All right, you can see the list of nuclides. These are fission products. These are activation products, and they are following these things, these nuclides. Do you have any idea what is missing here? You can see here, in the bottom of the list, there is something missing. Actinides, plutonium, etc. And this is political issue, I think so. Because if you know that you can characterize nuclear fuel or nuclear materials on the basis of course, by analyzing these, but you can calculate different things by analyzing plutonium isotopes, for example. But this is the list of the nuclides that they did monitor, but not transuranium elements. It's a political thing only, nothing else. All right. Then there are radionuclides from other sources too. For example, isotopes used in diagnostics and treatments. How many of you are using or participating in accelerator-related things? All right. But these nuclides are produced very often by using cyclotrons. This is a specific nuclide used in hospitals. Do you have here smoke detectors? You have. In Finland, we don't anymore sell smoke detectors containing americium. This is in fact a ionization chamber inside there. But there are a lot of other products like clocks, which are radioactive, containing radium-226, for example. watches, glass, jewels, light bulbs, camera lenses, etc. In the industry, they are using these nuclides, for example, monitoring surface levels of big tanks by using cobalt-60. Militaries, at least Yankees, they are using depleted uranium munitions. But then it is possible that some terrorists use malicious radionuclides in nuclear terrorism, I mean. Possible nuclides are these, and mainly based on source availability. All right, I think that this was the last slide. Do you have any question of this area? This is like an introductory material, so it's not very relevant on this course, but it's a background material.
Is it function 90?
Please use your voice so that they can hear.
I looked at the list of radionuclides in CTBT.
CTBT, yeah.
But strontium 90 was not included. So is there any
Strontium 90?
Yeah.
Yeah, indeed. But CTBT analysis or laboratories analysis gamma ray emitting radionuclides. This is the analysis techniques that is allowed in
gamma ray?
Yeah, gamma rays. Any other questions or comments? All right. All right. Shall we have a small break now? Is it possible to have? Yeah. Small break? Do you accept? All right. 10 minutes, 15 minutes or so?
Maybe 10 minutes.
Yeah, all right.
10 minutes. Because we have to break for lunch at 1 o'clock. And your next lecture is half an hour?
Yeah, around, yeah. So we will back 12:30.
Okay.
Yeah.
What is the time? Yeah.
Ah, all right.
And
Thank you for.
Have a short lecture and then we break for lunch. And afternoon we'll have one more session on the practical. Then we go to the lab.
Sir, will you share these slides?
Sorry?
Will you share these slides?
We are sharing the
Slides, presentation.
Yeah, it is already
Presentation. He's asking
Will
me
you
to
share
share the presentation.
Yes, Karunakar will send these later. Yeah. Yeah. Sorry.
Any questions? So my request again is make it as interactive as possible.
What about cancer patients in Finland?
Sorry, because this machine creates so much noise, I can hardly hear. So,
Cancer patients in your Finland. Any
yes,
comparison?
yes, there are cancer patients. Yeah.
What about
Sorry?
in the uranium deposits are available in Finland? Is any relation that is
In fact, I don't know that very well. But we don't have very much mines in Finland. I mean uranium mines. All right. All right, have a break.
You want full screen?
I will.
Yeah.
I will. Can we can we start now? Karunakara is missing, but maybe we can start if you like. You like? Shall we? All right. So, the title is Radionuclide Data. And this is very important that you understand the data. How nuclides are decayed and what kind of radiation comes out in the decay process. All right. After introduction, I will show you some data-related things and also web-based user interfaces. Maybe you have used some of these interfaces. So, this is very important slide, this one. I have grouped here analysis methods as different classes. Radiometric methods in the left, then microanalytical methods and some other methods. So, what is the advantage of using radiometric methods? So the point is that radionuclides, they actively send us information about when they decay. So we do not need to kick them and say that please send us information. They do it actively. And we can use, for example, direct or non-destructive alpha spectrometry. We can use gamma ray spectrometry, beta spectrometry, X-ray imaging or spectrometry imaging or fission track methods. We can use these without activating the nuclide itself. They actively send us information. What about microanalytical methods? We have to say to nuclides that please send us some information. Okay, I cannot say them that please send us information. I have to use protons or electrons or different kind of particles so that they can send us information. Methods are, for example, neutron activation. Particles are then neutrons. We can use X-rays. We can use electrons. And in fact, this SIMS is one part of mass spectrometers. So I think it's quite important to understand the difference between these two. So they actively send us information. We have to say to nuclides that please send us information. And then there are some other type of methods, like mass spectrometry or liquid scintillation methods or infrared spectrometry or whatever are the methods. And in this course, we use these methods. And also a little bit these methods too. Okay. So as I explained, I will explain this once more. Advantage of the radiometric methods, such as alpha or gamma spectrometry, is that we do not need to wake up the material we are analyzing. They automatically send us information. And if you want to calculate the activity, you will see this equation many times during this course. But we can calculate the activity in a very simple way. And this equation holds for gamma spectrometry and alpha spectrometry. So we have to determine peak area. We have to know efficiency of your detector. We will consider these parts later. We have to know now the nuclear data. And we have to know the measurement time. There are, of course, some corrections, but just now I will neglect these corrections. This is in fact very simple, not a very complicated equation. As I explained to you, Karunakara will later send you all these slides. All right. So these yellow circle quantities are determined or obtained from the measurement equipment or from the analysis program. This one. But this is from the data obtained from radionuclide libraries. But there are a lot of different libraries. So, which one should be used in the analysis? It's a very important question because not all libraries are good libraries. So, in fact, the basic emission data have been obtained from scientific publications. However, in very often cases, there are several scientific papers in which emission yields have been reported. But the yields are, or energies are, or maybe a little bit different in each publication. So, how to determine which data is the best? So, the original data, I mean these scientific papers, they have been evaluated by high-level experts, and the final data is gathered in a specific nuclide library. And this is very important because quality of the data is of utmost importance to determine radionuclide activities. So what's the basic data? Okay, I will basic library data. I will show it soon. Okay, let's go through the decay processes. So mainly we are in this course dealing with alpha or beta decay. Why not gamma decay? There is no gamma decay. You have to understand that. there is gamma emission. So nuclide itself is not decayed when gamma emission happens. So the nuclide stays same. Okay, this list is from the Wikipedia, and this is not a full list. I know that you have studied these kind of things in your universities before, so I will not go through these details. You can do that later when you get these slides. So, what happens? We have a nuclide to be decayed, nuclide X here in this case. It decays via alpha or beta or some other decay process. And here, for example, this alpha 2, beta 2 can go to the base lane. So there is no, what's the word?
Ground level.
Yes, it's a ground level state. Yeah. However, if it doesn't go to the ground level, it will go there very soon by emitting, for example, gammas, X-rays, Auger electrons, or conversion electrons. And these processes are typically very fast, less than microseconds. Of course, there are exceptions. But this is also very relevant to understand that these processes are really very, very fast. So, from the point of view of the present course, the main decay processes are these. This EC is electron capture. Do you know that? I think most of you knows, but it happens so that a decaying nuclide takes an electron from the electron shells, one of the electrons, and then proton converts to neutrons. And this process generates X-rays because the electrons must be rearranged in a new format. So you have to understand this. I already explained. So there is alpha or beta decay, but no gamma decay. No change of nuclides. Instead, there is gamma emission. So in the previous tables that I showed you in the presentations, in the previous presentations, so some of these emission yields are normalized to 1. So 1 per decay. However, gamma emissions, they are not normalized. So it may happen that 1 decay can produce, for example, 2 gammas. For example, cobalt-60. It's a typical example. All right. Let's go to the nuclear data. So there are several nuclide libraries, such as NSDF. You can click or use that link, NuDAT, and this is the data that radiation metrologists use. This is evaluated data, And I will show you how you can obtain this data. And as I told you, meteorologists from International Committee for Radionuclide Metrology recommends of using this data. There are several user interfaces like that. I will show this very soon, not now. It seems to be quite complicated, but it is very easy to use that one. There's NSTEF. You can try to use this link. NuDAT, nuclear data. Oh, this is not valid anymore. So this data is same data basically as in the LARA application that I will show you just now. Is it possible to take it away? I cannot connect to my computer to the net because of some security related things. My organization is very tight in this area. Okay, thanks. All right. Very shortly. You can select the nuclide in question by using this or by writing it down here. I put cesium-137 in the beginning. You can select here what kind of data you want to out, but I just say that, okay, show all data. Let's see what happens. So this is now the data. And you can see here the emissions. So as you know, cesium emits 661 kilo-electron volt gammas. But there are also some other gammas too, which are normally not detected by gamma ray spectrometry. But there are emissions of X-rays too. And for example, in this case, if you want to calculate activities to mass, for example, in this case, if I assume 1 becquerel, how much is it in terms of mass? Very low amount, 3 to minus 13 grams. I can put here, or can you suggest some other radionuclide? Which? Cobalt 60, all right. Let's try to use this one. Cobalt. This one, all right. It's maybe it's better to write it down. So all data. So these are the main emission lines coming out. Let's look at the activity to mass conversion. 1 kilobecquerel reverse to this much. If we try to use uranium, for example, uranium 238. So all data. So it's shown here. As you can see, there are no large amount of gammas going out. Close to 50, so the emission intensity is only 0.07. And practically these other gammas, you can neglect these. These are alphas here for MeV. And these are the information of the daughter nuclides, thorium and protactinium. No, very much data. It is because of the protactinium. Let's look at the, okay, and also other nuclides. I will cancel this radioactive chain, so all data, again, now there should be only, not only uranium, let's see, emissions, I select only gamma emissions. What happens now? Why it is showing, oh, so daughter nuclides, cancel this, so all data. Now, this is uranium data. 2 relevant gammas only. And they are not very relevant, in fact. So we have to analyze them by using daughter nuclides. Let's look at the activity to mass conversion. 1 becquerel refers to 80 micrograms. So if you if you need relevant nuclear data, please use this application. And if you are using some other libraries, please compare your libraries to this information.
Can I calculate mass to activity from here?
Sorry?
Mass to activity from here?
Sorry, because of the noise, I cannot.
Asking mass to activity.
Let's do it this way. I haven't tested this one. Mass, 1 grams. What happens? Oh. Very handy tool.
Sir, one more question. What's there after the intensity? If you talk of that energy, 49.55 kg in the table.
Yes.
49.55. What is there in the bracket? Is it uncertainty or something?
This is the uncertainty. This is
Uncertainty.
Yeah. This is the specific case how to express the uncertainties. It's not. I think it's no. Ah, there. Okay, it's functioning. Thanks. So it's a normal. Well, it depends what is normal, but in that case, 0.0697 plus minus 0.06 0.26. So it's a little bit strange way to express uncertainties, but All right, this is my presentation. I think it's 1 o'clock almost. Do you have any questions or comments? Of course, we can discuss afterwards. Please ask me later if you
Any
like.
questions?
All right. Let's have a break. How long is that?
Yeah, if there are no questions, we'll go for lunch now and we'll come back here at 2 o'clock.
2 o'clock.
2 o'clock.
Okay.
Is it acceptable to you?
Yeah, yeah.
And then we will have a lecture from him about the laboratory session, and then we go to the lab. Today our laboratory is mostly, familiarization of your equipment. You will go to the gamma spectrometry lab, alpha spectrometry lab, and you will also go to the chemical lab. And I also suggest all of you to go to, of course, it's not directly relevant to this course. We have one that also, because that the concerned research staff is traveling abroad from tomorrow onwards. So you just see that facility today, and that will give you a familiarization of the facility, and you will be doing a hands-on tomorrow. Okay. So we start the afternoon session by there is a small presentation, radiation measurement in a laboratory. Basics to the radiation detection.
Oh, thank you.
And,
Okay, thanks.
and
Thanks.
in which Roy will be brief about basic aspects of radiation measurement. Then, as I said, we will move to laboratory. We will show the facility, around the facility, and that will give some idea about what instruments you will be handling. Okay. So, Dr. Roy.
I got this one. Now you know me. I'm Roy. All right.
Sorry that we did not give you.
Okay. What do you feel about the level of previous presentations? Are they too much above your head or are they too low around? It depends on the beta energy. So, when you are monitoring environmental radiation, you practically have to do sampling. In some cases, it's not feasible, but usually you do sampling. Sometimes radioactive materials are present as discrete sources, as in this case. I think these are some industrially used materials. But sampling is often necessary in environmental cases. You can take samples from soil, from a surface, wipe sampling, from water, for example, and in this case, from a test tube and from air. This is an air sample, very small one. Okay, let's go through about detectors. So, different types of ionizing radiation detectors are used in radiation protection and also measurements in the environment. There are gas field detectors, scintillation detectors, semiconductor detectors, a lot of other type of detectors. And the choice depends on different things, which are, for example, where the radioactive material is located. Is it external or internal radiation with respect of your body? For example, in this case, they are measuring thyroid. Do you know what are the radio elements that are in your thyroid in a nuclear incident? Iodine, yeah. And iodine 131 is the most valuable, if I can say it this way, valuable nuclide. So the selection of the detector also depends on the environmental conditions. For example, in this case, something is measured. I don't remember anymore what is detected here, but there is snow outside. So in Finland, this is especially important because in the winter time it's cold there. Sometimes you have to measure contamination, and this is typical in laboratory conditions, because you have to follow that you don't disperse radioactive material all around. So you have to check the contamination of the lab. How often do you, in this laboratory, how often do you check the contamination levels? In this lab, yeah.
Every 1 month we use a handheld dosimeter.
Yeah, all right.
To check the
All right.
And in our radiation gamma chamber, there is a device outside.
Yeah.
So gamma radiation chamber, we checks every day,
Yeah.
like every second.
All right. Yeah. Okay. Then the choice of the detector depends, of course, on the radiation type. So in this case, they are measuring alpha radiation from an air filter. This is counter, not a spectrometer, this one. We can measure gamma radiation from the ground, beta radiation from a surface, or neutrons in different conditions. And finally, if you have to select between a counter and a spectrometer, in case of a spectrometer, you get out a spectrum. However, in case of a counter, you just put all the signals together, but you cannot identify the nuclides by using a counter in normal cases. All right. Then there are other type of detectors like these ones that should be used in some laboratories, not generally in environmental laboratories, because the dose levels are quite low very often. But in nuclear facilities, you have to use these kind of detectors. All right. Then there are some other things that influence the choice of the detectors. So one limitation is that what is the energy window or energy areas that you have to detect. So it depends on the thickness of the entrance window. Sensitivity of the detector is very relevant in some cases. If the radiation field is very high, for example in nuclear reactors, then this sensitivity is not necessarily the biggest, or how to say it, it's not necessarily important, but in environmental conditions when the radiation fields are quite low, then it's good to have a sensitive detector. One point is that is the detector appropriate for high contrast? Normal spectrometers, the count rate should not be too high. It depends on the size of the detector there. So there is so-called dead time. So if the dead time is too big, then you get out nonsense. One thing regarding the choice of the detector is this. Is it battery driven or how the detector is cooled? Then these are the things that are very important when you have to do measurements in the field. Size, weight. You cannot use these gamma ray spectrometers in this fixed laboratory outside of this building. You need a truck. But in the field you have to carry things. So robustness is one thing, easiness of operation, etc. Okay, let's have a quick look about the operation principles of the detectors. So, let's start with gas-filled detectors. So, this is a detector, this one, and there is gas inside. There is an electric field between the surfaces. What happens when ionizing radiation comes to the detector? It can come here from left, or from the top, or from the bottom, but positive ions, electrons are generated, and using voltage between the cathode and anode, we get the signal out. These so-called gas-filled detectors, they are classified in different, different type of detectors. There are ion chambers, proportional counting chambers, and Geiger chambers or detectors or counters. So it depends on the strength of the electric field. So in this area, we can in fact have we can identify energy of the radiation. These are not very good in terms of resolution, but we can identify the energy. However, if the voltage is high, typically 1 kilovolt or something like that, each photon, beta, alpha, or whatever coming to your detector generate a signal which is dispersed all over in the counter, and you get out signal, but you cannot identify the nuclide. All right, regarding ionization chambers, typical gases are air, argon with methane, etc. They are using quite low voltage. So signal amplitude is proportional to radiation energy. They apply quite well for gamma and X-ray measurements. So number of generated ion pairs, they are proportional to the gas mass and density. And you get more efficiency if you use high pressure gases in the chamber. There are some examples of small ionization chambers here, and also alarm systems, they use ionization chamber. Proportional chambers, they are like these ionization chambers, but they use intermediate voltage. So there is an electron multiplication, because in these cases, it may happen that because the voltage is not very high, the generated ions and electrons might combine together inside the chamber, so there is no signal. However, in these cases, there is an electron multiplication which is proportional to the original number of ion pairs. So it's possible to obtain energy spectrum of the radiation. So, in fact, we can measure alpha particles or low energy photons if the source is placed in the filling gas. And this is Geiger counter. I already explained that there is an electron avalanche which is not depending on the original number of ion pairs. All right. And as you can see, there are a lot of different type of Geiger counters. The point for this is that they are very simple to use. They are usually calibrated on the dose rates. For the energies quite close to cesium-137. Advantages are they are robust, simple electronics, low price, sensitive, and it is possible to connect alpha or beta probes together here.
Sir,
Hmm?
sir, all these Geiger counters can be used as a contamination monitor?
Yes, they can be. Not all of these, but some of them. It depends on the detector. Yeah.
Portable gamma radiation monitors is there. PRS.
Yeah, I think yes.
It is attached to GM counter.
Yeah.
GM cube actually. So can we it is used as a contamination monitor? It's a portable one.
There is I think they have a separate system.
Yeah.
So it's like a screen. I mean, this part of the detector present. So they are not necessarily Geiger counters, those contamination monitors. It depends on the case. And then there are scintillation detectors which operates so that radiation coming here or from the bottom, they generate photons inside here. Then there is so-called photocathode that makes this signal to release an electron, which is multiplied here, and we get signal out. These are the connector pins here. There are scintillation detectors here. So the electron pulse is proportional to the energy of the original radiation. So these are in fact spectrometers. There are a lot of different types of scintillation materials. There are organic, inorganic materials. There are also solid and liquid materials. These are the typical materials. Perhaps this is the most common material. And the good thing is that the density is high, which means also quite good efficiency of the detector. In this picture, we are testing lanthanum bromide detector, and I think this is sodium iodine, this is lanthanum bromide. This is a pressurized ionization chamber. But if you are using these type of detectors in environmental measurements, I mean outside laboratory, the problem is that they are sensitive for temperature changes, which makes energy calibration, it's not necessarily valid in different temperatures. And lanthanum bromide detectors, which are quite modern, they have quite good energy resolution, but there is intrinsic background coming from this nuclide. All right, now you can see spectra from different type of detectors. In the bottom, green ones, this is sodium iodine detector. I guess that the source was cesium-137, so this energy, and cobalt-60 here. And this is, I think, yttrium-88. I guess so. Now you can see the resolution, I mean energy resolution. Energy goes in this axis. Number of counts goes this axis. As you can see, in case of lanthanum bromide detector, the resolution is quite good compared to this sodium iodine. However, high purity germaniums, they will give us very, very narrow peaks, which makes possible to distinguish peaks which are located very close. For example, these two peaks here, you cannot resolve them by using especially sodium iodine detector. So typical density of high purity germanium is around 5. Same is for lanthanum bromide and sodium iodine. It's a little bit lower. But the point is that interaction strength is better when we have a dense detector. Interaction probability is higher compared to air. Do you know the density difference between air and, for example, water? There is a difference between 1,000, which means also that for the radiation point of view, it interacts strongly with dense material. Okay, there are some other things that I will not explain just now here. You can read these things afterwards. So, solid scintillation detectors, they are appropriate for gamma spectrometry. And liquid scintillation detectors, they are for alpha and beta spectrometry. But you have to mix the sample to the scintillation material. This means that usually the sample should be in liquid form, but not always. This is the comparison between sodium iodine and lanthanum bromide spectrum in case of iridium source. So the difference is not very big, but anyway there is some difference. Some years ago we tested how to use unmanned aerial vehicles like this one in environmental monitoring. We put a sampler here. We put a small spectrometer, this one, to the fuselage of the UAV. Before doing that, we compared resolution of different type of detectors. Here is a cadmium zinc telluride detector. Here is lanthanum bromide, sodium iodine, and calcium iodide detector. In fact, the best one today, I think it's a cadmium zinc telluride. But as you can see, in case of calcium iodine detector, the resolution is not very good. All right, then I tested also this very small detector. The size is some centimeters only. And we tested it because we intended to put this detector in this UAV, but we didn't do it. So, you can see the resolution, which is quite good. For example, in these peaks, there is not very much overlapping. But a question. So, are there any reasons to mount, for example, this kind of small spectrometer in a drone? Do you have any ideas? Of course, it must be a small detector because the drone is very small, this one. I think the size is like this one. Do you have any idea? Okay, if you are looking for example, nuclear fallout, and these kind of vehicles, they don't go close to the ground. They stay quite up, 100 meters around. Then, if the detector is small, you cannot detect practically anything. However, in case of a nuclear accident or incident, when the radiation level is high and there is radioactive material in air, then it's an advantage to have a small detector because dead time may be quite large in case of a large detector. All right. So these spectra are from the EU 252. The source is located here. This is the sodium iodine, lanthanum bromide detector, and this is this CHROMEC detector, very small one. Mass is very small. Now we got the point. Alpha and gamma spectrometry. You can see alpha detectors, not spectrometers. Detectors here, they are more or less spectrometers here. These are germanium detectors with different shapes. There are cooling system here. The detectors are here. There are different type of systems. These are electrically cooled here. So the operation principle is more or less same as for the ionization chamber, but instead of mobile ions, radiation produces free electrons and holes in the semiconductor material. And they are around 10,000 times more sensible than gas-filled detectors of the same size. And because of the higher density. They can be applied in alpha, beta, gamma, and X-ray spectrometry, depending on the energy of these and the radiation type, of course. So, typical semiconductor materials are silicon and germanium. They are doped with impurities to create either N-type or so-called P-type conductivity. So ionizing radiation, which are traveling through the detector material, produce free electrons and holes. I will consider these interactions in later presentations. But the generated electrons, they are transferred from the valence band to so-called conduction band. They can move there, and an equal number of holes and ions, electrons are created. They are collected and separated by using internal electric field. Electrons move toward the anode and holes toward the cathode. So, the number of electron-hole pairs is proportional to the energy absorbed into the semiconductor. A pulse is generated whose magnitude is proportional to the energy deposited by the radiation. In the left you can see a typical alpha spectrum, and in the right, typical gamma ray spectrum. So, do you have any comments why they are so different? Of course, energies are different. You can see that the typical alpha particle energies are quite close to 4 up to 9 MeV. Typical gammas are quite close to 0 up to around 3 MeV in case of natural radionuclides. So there are differences in the spectra, and these depend on the radiation characteristics, how they behave in the detector. The peaks are more or less same, but there is a difference between the background. Do you have any comments on this? Okay, if not. So, in case of photons, you have to remember that the energy is always the same for each photon. For example, for cesium-137, it emits exactly 662 kiloelectron volt photons. However, in the detector, the signal is different because of some things that I will explain later. And according to some of my previous slides, the endpoint is spectrum, gamma ray spectrum. Peaks are relevant. These are not relevant here. They disturb the analysis, in fact, but we have to take them into account in the spectrum analysis process. These things will be explained later in the laboratory and also in next lectures. So, what are the differences between silicon and germanium? So you can see the charge number is by a factor of 2. There are some heavy or dense materials also. I haven't tested this kind of detectors. Never. You can look at these things later, but this is a typical alpha spectrometer. I mean high resolution alpha spectrometer. And, there is this part of the detector is sensitive for radiation, and thickness is around this size, sub-millimeter size. So, do you think is it good to have thicker alpha detector? Who says? Yeah. Can you explain why? Yeah. Yes. That is one point. That is one point. Did you hear that? So, one point is also if the detector is thick, then it can detect also gammas, X-rays, and other particles, which makes difficult the analysis. That's why it was optimized to be very, very thin. Regarding gamma detectors, there are different types of detectors. What kind of detectors you have here? In STUC we have these planar or thick planar detectors. We have also one well detector, mostly P-type of detectors.
We have one N-type and two P-type.
One planar and two P.
Yeah, one
yeah.
N-type and two P.
All right.
What is a P-type coaxial? What is a P-type coaxial?
Hmm?
P-type coaxial
Yeah.
type we have.
No, you have. All right. We have also this kind of a well detector. So you can put your sample, which is generally a test tube. Basically, if this detector is very large, you can put this inside the detector. But what I have found is that there is a problem of coincidence particles, and it is very difficult to take into account in case of well detector. I will explain this later, but okay, these are good detectors, of course, because of what? Because of the high efficiency. Because all the radiation, if the beaker is in the bottom of a well detector, so practically all gammas are detected. However, in case of planar detectors, most of the gammas are coming out of the detector. So the terminology is geometrical detection efficiency. It's high in this case, not very high in these cases. However, these are very good detectors in general. All right, then there are a lot of different detectors. For example, films or imaging plates, they are very useful. In this case, I remember that it was almost 30 years ago when I did autoradiography. I got a sample from one of our nuclear reactors, and one of my colleagues wanted me to analyze that sample, and the purpose was to check that how radioactive materials are dispersed in the filter. So you can see that each of these black spherical areas, they shows the location of so-called hot particles. So it's now I forgot the concept, but it's a quite non-homogeneous case. Usually it is assumed that your samples or whatever you are measuring, they are assumed to be homogeneous. Okay, some slides about radiation protection in the laboratory. Please take these things into account. So you have to stay away from active sources. You should use shields when the source is active, and it's a good way to keep some distance. You know this thing already. So in some cases you might need these in environmental monitoring, but this is for the nuclear accident. Normally you do not use these kind of things. However, in case of a laboratory, you might need these ones. Do you have any idea what's the source here?
What kind of source is being used? Alpha, beta, or gamma?
What is your suggestion?
Yeah, answer. How many of you say alpha? One. How many you say beta?
I mean, I don't know the source, but it's not useful for gammas, at least high energy gammas. For in the case of X-rays, this might be good, but for betas, this is perfect. And especially if this is plastic, why not glass? It is because of so-called Bremsstrahlung. Because if the electrons stops very quickly, Bremsstrahlung, it's a very difficult word. It's coming out from the shield, and it generates, of course, doses. So it should be plastic or something like that. All right. I think this is one of the latest slides. So when you are working in the laboratory, you have to know the doses that you receive from radiation, and effective dose is the main quantity that is important, also equivalent dose is important. And they depend on the radiation type, energy of the radiation, type of tissue. And effective dose is the weighted sum of organ-specific equivalent doses, and the unit is sievert. It is calculated like that, very simple. But in fact, very complicated to determine, basically. All right, and different quantities are needed to characterize the doses. There are several other type of doses, and especially this effective dose. This one cannot be directly measured. However, we can have an impression of the dose by using, for example, Geiger counter, which is well, basically not calibrated to the effective dose. However, you have to do sampling to evaluate these parts. However, you cannot do sampling from your colon or lung or liver. It's not possible, of course. Maybe afterwards. Okay. Okay, this is it. I hope that this is okay in the beginning of the laboratory session, and this is only, as I told you, very brief introduction. Okay, thank you very much. I don't have. I don't have questions. Sorry, because of this noise, I want to go closer. Yeah.
You said in accident conditions, if there is an accident condition, small detectors are preferable. Can you explain to it as why we are requiring small detectors?
Yes. It depends on the
kind of radionuclide, or?
Yes, but also if you compare the detector sizes, and if the radiation feed is very strong, you get too many signals to your detector. Especially spectrometers might be non-useful in those cases if the signal level is too high. Then it's better to have a small detector. However, detectors like here, they are good for detecting environmental radiation, because the signal, the amount of signal or density of the signal, it's so low that they are very good for that. But you cannot put high energy, high actively source close to the detector. It is so-called dead time. Is it? Do you think is this okay? All right. Any questions? Okay, but if there are no questions, you can ask me later. So
Yeah. So, no more questions. We go to the lab. We see the various equipment. So definitely we will be spending 2 hours in the lab to see the facility, and tomorrow we will start it. And if you finish today early, then we may start to do that's what, yeah. So you should see that also. So try to spend as much time as possible, and there is no afternoon, evening, there is no limitations. You can be here in the lab up to 9 o'clock. we have shared the group details already. So accordingly, batch 1 and batch 2 go to gamma spectrometry. So today we'll make one thing because they want to go to radon calculation. Batch 1 will go to gamma spectrometry, batch 2 will go to upper spectrometry, batch 3 will go to radon. Batch 3. Okay.
Alpha spectrometry and gamma spectrometry, like radon is on the top.
Right.
So group 3.
And when you finish, we have there could be beryllium window and aluminum window. Is it not? Yeah. We use composite carbon because composite carbon is a better material which allows the both low energy as well as high energy carbon. So that's the reason composite, and it is this composite carbon material is very sturdy. So this detector has a nominal efficiency of 50%. And when you talk about a HPG detector or for any nuclear detector, the important parameters that characterizes is its efficiency. So this has a nominal efficiency of about. So you normally classify the detector in terms of relative efficiency. Previously we used the relative efficiency because sodium, in comparison sodium iodide, what is the efficiency of this? So sodium iodide was considered to be one time the high efficiency detector, benchmark detector. Then later this came. So you compare the efficiency of HPG relative to sodium iodide. Subsequently, they started, reporting it as nominal relative to sodium iodide. Relative is nominal means among a group of detectors, if you measure the efficiency, what is it? That's it. So that is the one parameter. Efficiency is the one parameter which characterizes the detector, important parameter. Second one is the minimum detection level. Of course, you will be calculating the minimum detection level for each of these detectors. You will what is the minimum level you can detect with the minimum level of a gamma active radionuclide. You can detect with this detector. That is another parameter. And the third parameter is background. What is the background of the detector? Suppose because even if there is no source, the detector will give you some count, right? Yeah, some count. So what is that count? Because lower the background, better it is. So that's why the detector is provided with the shielding and with advanced electronics. For example, you see this detector is the shielding is flushed with nitrogen. You have come across such devices? This is nitrogen being flushed inside the cavity of the thing. You see, there is a gap between the detector and shielding. You see here. University. Detector is there and there is a cavity. This is the gap. Okay. So there we always flush nitrogen. That is because to reduce the background. So normally what happens, this air gap will have radon as well. So this radon is progeny. Yeah, radon progeny will accumulate. That builds up the background. So we don't want that radon to be there. So that's why this nitrogen, the nitrogen in the gas form. Liquid gets converted into gas. Mapping ಮಾಡ್ಲಿಕ್ಕೆ ಅದು ಅದಂತ ಹೇಳಿದ್ರೆ ಅದರಲ್ಲಿ ಅವರ ಡ್ರೋನ್ ಅಲ್ಲಿ ತೆಗೆಯುವ area. So that's how you reduce the background. So ಇದು ಸರ್ವೆ ಮ್ಯಾಪಿಂಗ್ ಅಂತ ಹೇಳ್ತಾರೆ. Relative efficiency and then minimum detection level. Of course, minimum detection level. ಅದರ ಐಡಿಯಾ ಇಲ್ಲ ನನಗೆ. ನಾನು ಯಾರತ್ರ ಎಕ್ವಿಪ್ಮೆಂಟ್ ಯಾರತ್ರ ಇದೆ ಅಂತ ನೋಡಿಬಿಟ್ಟು ನಾನು ನಿಮಗೆ ಹೇಳಬೇಕು. Of course, your electronics. So this is the basic detecting side. Idea. We have electronics too. ಜಾಗದ ವಿಡಿಯೋ ಹೀಗೆ ತೆಗಿಲಿಕ್ಕೆ ಬರುವುದಿಲ್ಲ, ಅದು ಮ್ಯಾಪಿಂಗ್ ಅಂತ talking in detail. And we have 3 high purity germanium and 1 sodium. Of course, he has already said the difference between sodium iodide and high purity germanium. What is that? ಜಾಗದ ತೆಗಿಲಿಕ್ಕೆ ಮಾತ್ರವಾ? ನಾನೊಂದು ನಂಬರ್ ಕೊಡ್ತೇನೆ. So efficiency of course is high. And the main is resolution is the one which is an important parameter. Because here ನಾನು ಡ್ರೋನ್ ಇಲ್ಲ, ನಾನು ಡ್ರೋನ್ ಸೇಲ್ ಮಾಡಿ ಸುಮಾರು ಟೈಮ್ 100 isotopes, gamma isotopes. You can determine all of them. Whereas in sodium iodide, you will not be able to distinguish two closely lying peaks. Right? Yeah. ಅದರಿಂದ ನನಗೆ ಒಂದು ಹಾಯ್ ಕಳಿಸಿ. But it has its own advantages, which we will discuss with you
ID card ನಮ್ಮ
So you
pump
can
file
see
ಅಲ್ಲಿ
these detector spectrum. Some of these show them the uranium thorium spectrum, potassium spectrum.
ಆಂಪಲ್ ಏನು ಸರ್ ಅಜಯ್ ಕುಮಾರ್ ಅಜಯ್ ಗೊತ್ತಿಲ್ವಾ ನಮ್ಮ
Yes, and GAN.
ಸೆಕ್ರೆಟರಿ
So as such,
ಓಕೆ
you want to give them? Yeah. So as sir said, so we have three high purity and one sodium. Okay. Now basically I want you have understood basic aspects of this detectors. The background correction. So whatever the detection it is, let us say alpha, beta or gamma, background correction is must. So what is background? So background is a radiation level that is already present in the air. But when it comes to detector, how much of this background gets inside the detector so that it is detectable. So it is same for sample as well as when sample is there also you get background. When without sample also you get something. So we have to subtract. Or else unnecessarily some counts will add it up. Unnecessary things will add. It is not countable. Yeah, it is countable. We don't want to count. So we keep an empty. Yeah. So for example, if this is my sample, so this is a thorium sample, RgPH. So if I will keep an empty bottle of the same inside and count the background, then I get the background of this plastic bottle as well as environment. So other ways to reduce background is this shielding. So this shielding is special because you might have seen already. Basically, people use brick shielding, right? Lead bricks to shield, but this is molded. So because it is molded, you will get This is also lead, not lead bricks. Yeah. This is molded. Molten lead is molded into this, and this is 10 centimeters. So because of this, background is very less. So that is why we call it as ultra low background detector. So background is very much less. So whatever the comes to it, most of it will be there from the sample. Most of the times we get 1 or 2 counts for the sample. So because of this, you can see the minimum detection level. So minimum detection level for cesium in this detector is almost, sometimes we get at about 0.1 becquerel per kg. So 0.1 becquerel per kg, you saw how much is 1 becquerel of cesium. 1 becquerel of cesium is 1 into 10 power minus 30 grams of cesium. So that much small activity we can detect. 1 becquerel is 10 power minus 30.
direct mic
0.1 would be again 10 power minus 14. That much minute activity is also detected. Now this is basics about the background. So once we have done that, then there are different types of detectors in HPG. So you have well type in the sense it will have a hole in the liquid and 360-degree counting. Then coaxial detector, which only detects one side. Each one has its own advantages that you will learn during the course of this. Yeah. So this is coaxial. That one is well type. So different types we can use. So we use HPG basically coaxial. So each has its own advantages and disadvantages that we learn slowly. So this session is only to familiarize with the stuff. So now this is HPG liquid nitrogen. So why do we need liquid nitrogen? You might have already learned why. Why do we have to cool? Yes. So semiconductor, semiconductor behaves as a conductor at room temperature. So how does this an HPG work? So you basically have a PN junction diode. Okay. So you reverse bias it. When you reverse bias this junction diode, there is a large amount of depletion, large area for depletion region. So when radiation falls on this depletion region, each radiation will correspond to certain amount of current. Okay, an electron hole pair is generated and that will constitute electric current. Okay, that current is then made it into this spectrum. I'll explain how. But if the detector is kept at room temperature, in addition to this count, there is large number of thermal electrons that is generated. That also gives electric current. Now I don't know how to separate these thermal electrons with this. So because of that, we keep it at minus 178 degrees Celsius by using liquid nitrogen. Okay, 169. Sorry, 169. Some say 178. So somewhat around minus 170 degrees Celsius. Okay, that is the temperature of liquid nitrogen. Minus 170 degrees Celsius.
Yes.
Or 100 Kelvin.
Yeah, approximately that amount. So this is the need for liquid nitrogen. Oh, this is only required in semiconductor detectors. So you can see that sodium iodide does not have it. The principle over there is completely different. I'll explain after we finish this. Okay. I hope sodium the scintillation detectors has been taken in class in the last class. Yeah. So now coming from, so I have got a signal. You understood signal is generated, right? Now this signal has to be converted into these peaks. How do you do that? So basically, if I for any kind of signal you need amplifiers, correct? So your amplifier is over here. My amplifier, main amplifier is over here. Now during the transmission from there to here using large number of wires, these electric signals are very minute. Okay, very small electric signals are generated by the interaction of radiation with this semiconductor material. Now while transmitting it from over there to here, generally there will be a lot of other like noises generated in the cable, correct? It will be there. So how do I remove that? What to do for that case? Any idea? Yes. So we keep a preamplifier here itself near the detector. So this wire comes from the preamplifier itself. So inside the detector there is an amplifier. As soon as the signal is generated, within the least amount of distance we amplify it. A small amplifier, yeah. So to some extent, that is what we call it as preamplifier. So that is then transmitted to this. This is a preamplifier plus MCA. So it has MCA is multi-channel analyzer. Again, that has been covered.
No, they didn't cover
Okay,
MCA
okay,
and
yeah.
all.
So amplifier. So here we amplify it, and now you have signals. Basically, we have so many signals, each of specific, let us say, current. Okay, or specific voltage. You have current like current by current distinguishing and voltage distinguishing systems. So either one of them is used. So now suppose we have a separate voltage. So now I have to assign, the system has to assign one voltage is equal to 1 keV. So we have, this is 32,000 channels. So 32K MCA. 32,000 boxes are there, digital boxes are there, in which I can assign one box is equal to whatever I need. So we have assigned here one channel is equal to 0.25 keV. That means four channel is equal to 1 keV. Understood? So I can distinguish, that means this system can distinguish between 1.25 keV and 1.5 keV. So 0.25 keV we can resolution is there with the system. So each signal it comes, it will put into different boxes. So whatever the, for example, signal is coming of 100 keV, 10 signal is coming, so it will put into 10 into 100 keV box. This box is not this box, but I am just saying a computer storage unit. Okay. So now let me show it here practically how it looks. So this is a spectrum of uranium. Okay, if I'm, yes, this is a spectrum of uranium. Now look at this. See, there is one peak over here. So these are background levels. Okay, these are all background levels. Now I'm getting a peak over here. Now let me check what is the peak energy. So when a so we have one peak and there will be small tail to the either side. This will not be a sharp peak like XRD. Have you seen XRD peaks? It is very sharp. This will get a Gaussian curve, because of there will be small amount of activity or small amount of current be put into each other boxes. So now this is 46.5 kilo electron volt. Now I can identify what is, I know 46.5 is generated over here peak. So I can identify what 46.5 is. It is basically lead to tin. Okay. Similarly, then I will take the area of this peak. For example, just pay close attention. This will be taught to you in the class, but I am just giving you a brief introduction about this. So I can zoom in and zoom out. So this is a, can you say that, can I say that this is the start of the peak? Can I say that this is the start of the peak? So I'll put a marker over here. Okay, then I'll take the other marker. So this point I have put over here. For your easier understanding, I'll make it into bigger peak. Okay, So I can say this is the start of the peak, or I can say this is the start of peak. Understood? So this one, shall I put it over here? Correct? Okay. So this is our peak area. Okay. This much counts we will take. So this area consists of 80,887 counts. Okay. And that is for 60,000 seconds. Okay. Then using that formula, counts per second is counts net area. This net area divided by the counting time, CPS into 100 by yield of this peak, that is 4.6, I guess. I'm not very sure, I just have to say. Somewhere we get it from literature, into 100 by efficiency that I have already calculated, that we will teach you later how to do. Into 1000 by weight, I'll get weight of the sample, I'll get what is the activity of lead to 10 in this.
How do you identify that this peak is lead to 10?
Yeah, that is what it is given in the literature. I hope sirs showed you one library in the morning. Do you remember? In that library, we get we know that this energy corresponds to this peak. Okay, 46.5 is always lead, but sometimes some radionuclides, let us say bismuth 214. Bismuth 214 has 10 peaks, maybe more than that. So many peaks are there. You have 604, you have 1764, you have 352. So many peaks are there. So if either one of the peak is missing, I cannot say that it is bismuth 214. All the peaks should be there. So this is how we identify. Okay. Cobalt 60 has two peaks. 1131 and 113, yeah. 1.13 and 1.17, yeah. So two peaks are there for cobalt. Cesium has only one peak. So using this we can identify what is this peak, and then we calculate, using this we can calculate what is the activity of this peak using the efficiency calculation. How do you do efficiency calculation then? Any idea? You might be already knowing. So how do you do that? So for example, we get any kind of instruments you have used, sir? No, any what other instrument you use? UV visible?
No, that are actually mass spectrometers.
You are using mass spectroscopy?
Mass spectrometer.
Which one?
They are very low efficiency.
Which one? Which mass spectroscopy?
Mass spectrometer. These are IRMS.
IRMS, okay. So it gives elemental concentration?
Not elemental. They give the ratio of molecular weight.
Molecular weight. Okay. So here, have you used ICP-MS, sir? No. Okay. Or XRD. Okay, XRD might not. UV visible you have used? Okay. So basically what I am trying to say is that in any kind of spectroscopy analysis, you will get something called as a reference material. So ICP-MS, you have a reference material. It is generated by NIST, National Institute of Standards of Measurement, something like that, from USA. They have the reference material. For us, reference materials are usually from IAEA, International Atomic Energy Agency. So this, whatever I showed, is a reference material from there. So they will use the same sample, calculate multiple times for years together, and then they will say that this is a reference material, this is the value. Okay, for this peak, for lead to 10, this is the value. For uranium, this is the value of this peak. Now I keep this sample, I'll take the count, and using the formula, the this efficiency is nothing but CPS, that is counts, same counts, into 100 by activity, because it is in percentage, into 100 divided by abundance, yield. I'll get efficiency on percentage of this peak. Okay, that efficiency I'll use in the later stages to count the samples. So that is why while you doing HPG analysis or sodium iodide gamma spectrometry analysis, your sample geometry and your standard geometry should be same and should have the same density. For example, if you are using standard water standard, or even like if you are using sand standard, and if you are using soil for your analysis, your results will vary largely.
Okay, so you have to standard and sample should be
Same. I am saying the density should be same. The material composition should be same. For example, sand should has its own standards. Soil has its own standards. Water has its own standards. Filter. Yes, yes, yes. For vegetation, for example, banana, it is, clover is there, IAA clover leaf is there. Then you have, so spinach is there. Then so many things are there. I can give you a whole list. So we have around 20-25 standards here. So each sample is different for us. So you give us one sample, it is different for us.
So every time the IAE standard also?
Yeah. Sample density and your standard density should be comparable if it is not same. I cannot use water standard and then use a soil standard for counting. Yeah.
So every time you use IAE standard or you have the laboratory standard?
We always use IAE standard. We don't compromise on that. So we have IAE.
So similarly in mass spectrometry also, we are doing the stable isotope for water. So we also have the IAE standard.
Oh, okay.
And then we prepare the lab standard comparing this IAE standard because they are very expensive.
Okay, but no, IAE is free. IAE standard for us is free. No, for all the radioactive measurements, it is free if it is available. Only shipping charge is what we have to pay. So that is what I know, but maybe it might be different for different cases. Maybe it might be different. So we use we have standards from 1990s onwards. So from here, whatever the standard that comes, sir has bought it. So we don't have to worry. And every year we participate in something called as international inter-laboratory exercise, inter-comparison exercise and all. So for using, they send us samples and all this. So you might be knowing. Yeah. So because of that, we can say that our results are standard. So this is all about HPG. Any doubts? See, you take the peak, you get the counts, net area, you can see the area. So this net area is the addition of all the peaks. So here you get counts is 2579. Can you see here? So this peak. So next channel 459, channel number 459 gives you 2847. Next channel 460, 3218. Addition of all this will be there in this area which I have selected.
Other peaks are, what elements are other peaks?
So other peaks. So these peaks we don't identify. This peak also we can identify, but I go for very prominent peaks of it because see here these peaks are so close together. So if I analyze, for example, here you get a 63 peak which is of uranium. Okay, I think thorium-234's daughter should be, it should be something over there, but I don't use this because there is like lot of interference, spectral interference, especially over here. See this peak, I don't know whether it has ended or it has spilled into the next adjacent peak. So instead of that, I go for the very well separated peaks. So this is 186 is of radium-226 and this one 242 is I think lead-214 if I am not wrong, but yeah. Oh, no, 241 is another lead. Lead has so many isotopes. So many peaks. So again, this is 295 is again lead-214. So many peaks are there. So I can use any one of the peaks. So for the best results, what we do is that we analyze 4 to 5 peaks and see whether the results are comparable, and take the mean and give the standard deviation. So that standard deviation will be 1 sigma. We can give up to 2 sigma. 2 sigma levels we can give. That is 1 sigma is 1 standard deviation, 2 sigma is multiplied.
Activity of all the isotopes or only uranium? How do you give the results?
So for example, you are an user, you will say that I want only lead. I would not look at any other peaks. I will only give you lead. Suppose if you are asking for cesium, I will give you only cesium. But if a user asks me, give me K40, give me thorium activity, give me uranium activity. Uranium, in the sense we cannot, you might be already knowing, uranium we cannot identify using HPG. What we do is that we keep a sample, pack it and keep it for 28 days like this. So that time what happens is that radium and its daughters will come in equilibrium. Okay. So then its daughters, bismuth-214 and lead-214 peaks we will get. That using that we will give you radium-226 results. Yes. So radium-226 results we will give you. We don't know radium-226 is in equilibrium with uranium. If it is in equilibrium with uranium, then both are same. but we don't know that, we cannot establish that. So we don't give you uranium-238 results in HPG, we basically say it is radium-226 results. Okay, that we can give, that peaks are there. So radium-226 again, bismuth-214, lead-214, you can understand. So this is just an introduction. Basically in after like in a second session or third session, you will have to do this, that time you will understand. Okay, then you can get cesium-136. These are all naturally like cesium-137, naturally, like what are being asked by us so far. So you can also if you go for the like nuclear installations, there they will analyze americium-241.
I'm not working
Okay, they have another other, yeah,
K40, uranium-238
and thorium,
and
yeah,
one more I think thorium and
cesium-137 you do.
these four isotopes I remember.
Yeah, lead you won't get in sodium iodide.
No, they also have HPG.
Okay, but yes, if they have an HPG, if it is a carbon window, you get that peak. If it is not a carbon window, you will not get that peak. So yeah, so basically this is it. So any other questions? So if there is no questions, we can go to sodium iodide. Okay, I hope this is clear. Introduction wise, this is clear.
Can you just keep one sample and acquire and show?
It will take long time, ma'am. It is like 30,000 seconds. This is 60,000 seconds counting time. So yeah.
You can give that cobalt 60 or 60.
Yeah, we can give you. So this is already counted. So we keep the sample inside, the same sample, something like that. Soil samples we keep inside, we close it and we give count. Tomorrow morning it will be counted. That's it. I don't have to do anything else.
You are not even the reference cobalt 60 or 60.
We have. So that is a reference material. That is for the reference material. You mean say that disk that is also there, but that is very high active. Yeah, it is like we have 38 kilobecquerel active. For us environmental samples. So we say that like anything over than 1 kilobecquerel for us it is. Yeah, microcurie level it is okay, but I don't keep. So if yeah, the dead time will be more in that time. No, we can keep. I can show you. That is not a big deal. Maybe tomorrow or day after tomorrow I can show you if there is time. That is not a thing.
Sampling price, how much?
This one per sample we charge 2,000 rupees in HPG. Okay. Because the main cost goes to liquid nitrogen. Liquid nitrogen is very costly in the sense every week we need around, for 3 HPGs we need 100 liters of liquid nitrogen. Approximately. 1 liter costs around 40 to 45 rupees, or sometimes even it goes to 55 from outside. So that is what. So cost goes to maintenance of the instruments. 1 liter is approximately 50 rupees. You can say 50 rupees per liter. So 100 rupees, 100 liters per week. So yeah.
Some more P-type, some more N-type.
Yeah.
Choice.
That is depending upon how you want. It does not make a very much difference. So when we are buying, for example, when you are buying one detector, we mainly see about that nominal efficiency, whatsoever called, how much efficient it is. So now you have 100% efficient detector. That means 100% of what sodium iodide is giving, that it will give. So always previously they used to say relative efficiency. So relatively that was the thing. Efficiency was mainly seen, but this P-type and N-type will not make a huge difference as a user. But cost-wise, I don't know. N-type might be costly, yeah. Which one?
Planar detector XLH.
Yeah. Okay, maybe I'm not very sure. Okay, then yeah. Done. അത് കാട്ടിലുണ്ട് കാട്ടിലുണ്ട് അത് ആടെ കൊന്നിട്ടുണ്ട് കാർട്ട് എടുക്കും അവളുണ്ട് ഓക്കെ. So now let us come to, I hope HPG is clear. Okay, now we'll come to sodium iodide. Yeah, no problem. What happened to this PC? I think it went to sleep mode. Just give me a second. Pause one play. So before that, I'll show you the other two HPGs. Let me load it. I think it was switched on. Yeah. So we have another. This is an oldest HPG, as sir told. This was procured, I think, yeah, in 2003 or so. So it is still working. Huh? Yeah, yeah. That is 2015. This is 2008. Which one? Yeah, that's what we said. 30 onwards we can measure. 30 keV onwards we can measure. Up to we have kept the the last peak that we are measuring so far is of thallium 208 at 2614. That's it. So we keep around 3000. We have kept at 4000 kV. This is 32K channel, so I can keep even up to more than that, but it is of no use. So 2614 is the last thing that. Yeah. 16K is also done. So these two are 16K. These two are 16K. So in this you can see the electronics clearly. So here we have the high voltage power supply. Okay. This is the amplifier. This is the MCA, multi-channel analyzer. So all three are different. So this voltage we have supplied is 4 kV, 4 kilovolt. That around 4.5 kilovolt. This one is minus 3.5 kilovolt. Okay. So this is a spectrum similar. No. This is N type. Those two are negative charge. Yeah. So I'll just show you sodium iodide. So the main difference between HPG and sodium iodide is having less resolution and more efficiency. Efficiency of sodium iodide is more. So you can see that the sample which I used 60,000 seconds in that, I just need to keep 30,000 seconds, like 10,000 seconds here. So still it will give you a very good result. But for example, okay, the same sample, uranium sample. Okay. Yes. So it's loading, it's taking some time. Yes. Okay. So you can see that. So I have preloaded ROIs, ROI in the sense region of interest. So peak, this is 609 keV. So you can see that you are getting one peak over here. Okay. So you can see that in there the same sample, you can see the spectrum has so many peaks, correct? But here you have only, like, countable 1, 2, 3, 4, 5 peaks. So the efficiency, although it is higher, or if I do better resolution even then, so here the first peak I am taking is of 609 bismuth peak. You might be already knowing that. Beyond that you don't use. There I can start from 46.5. Here I will start from 609. So prior to that, all the peak I am just leaving. I just don't count it. So from here onwards, you have this is 795, I guess, and then this is one more peak. So basically, and one more thing, okay, can you see any other differences between this and that? Something based on spectrum. Look at this. Background is different. Something else. Resolution, yeah, and resolution we already know. Something else. See, some differences there between that spectrum and this spectrum. Just looking at the spectrum. That is resolution. No. Look at this curve. This is Compton effect. So this is a Compton scattering. So this peaks so this is for example, this one is thallium 208 peak over here, which is not present in the sample. That will contribute to the previous peak. So there is some contribution of present. If there is a thallium 208, it will contribute some activity to its previous peak, that is bismuth 214. Now again K40 will be K40 peaks count will be there will be some contribution from thallium and also bismuth. So additional peaks will have the peaks which are in front of the higher energy peaks will always contribute to the lower energy peaks. So we have to make a separate calculation to suppress this. Okay, there that issue is not there. Their Compton correction is done by the PC itself, done by the software. I don't have to worry about Compton correction. Here we have to do Compton correction. Okay, and again this is a scintillation detector. Working is different. There is a 3x3 sodium iodide crystal, thallium doped. So their electrical signals is generated by the reverse biased diode. Here, because scintillations are produced when the radiation falls on this material. Scintillation means flashes of light. So that is then converted into electrons by a photocathode. That electrons are then multiplied by a photomultiplier tube. Then that final counts are taken, and then we get a spectrum like this. Okay, so this is all about sodium iodide and high purity germanium detector. Any questions you can ask?
So this is well type.
This is well type. You want to see it? So I have kept a sample here. So this is the well over here. Can you see that? This, there is a hole.
Okay.
This is a well. So I can either keep the sample on top of it, or if I have a very small sample of this diameter, I can keep inside it. Okay. 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 Yeah. Okay, that's it. Any doubts? Any questions? No? So if there are no questions, I assume you have understood everything, or I can assume you have not understood anything. So I assume that you have understood everything. So if you have not, please come and ask at any point of time. I will be here, or you can ask anyone among us. Okay. Okay, sir. Then can we move to the next lab? Yeah. 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 Fine. The questions not only raises. Yeah. When you ask questions, it's not only increasing your knowledge, but also it will increase our knowledge also. Sometimes some questions will make us think a lot. We also might not be knowing some minute details. Sometimes some visitors ask, and then we'll think, oh, this can be thought like this too. So yeah. So that is why questions are important for both of us. Yes, then we can move to the next lab. Okay. Thank you. Thanks a lot. Yeah. You have a question?
It's a radium. 186 is a radium peak. We measure the daughter plate.
But we don't measure 186. 186 is not always present. Yes.
This is equal to activity of daughter
ಆಗುತ್ತೆ ಬರಬೇಕು ಬರಲೇಬೇಕು ಬಟ್ 186 yeah.
I have never used this kind of instrument.
Okay.
So I have so many basic questions.
You ask me any number of questions, I will answer. Okay. Basic, it doesn't matter. No question is basic. No question is advanced.
No, basic is like
no problem. No problem. Yes. You can ask the name. Again, I will come. You can ask the question. Okay. Thanks a lot, sir. One minute. No, it's fine. It doesn't matter. No, I just told you that there should be some order, right? So, I will cover one palete. Anda. Anchana. Okay. Okay, okay. Mittil onjittu. Mittide elle pay tu kasandarichi. Arijeri. Tondarichi. So yeah. So you are coming from alpha and beta. So you have seen alpha and beta measurements, right? So both places you have to do some kind of sample preparation, right? There should be some kind of digestion, some kind of conversion. So this is mainly because of their penetration. So alpha and beta are least penetrative. So we call these methods as destructive techniques. Okay. So those are destructive techniques. So once the sample is analyzed, it is lost. You will never get it back. But there is another type. Easiest of all the easiest way to measure radioactive element in a sample is by gamma spectroscopy or gamma spectrometry. The reason being, it is highly penetrative. You don't have to like use any kind of methods to calculate its activity. So for example, tomorrow you bring one sample to me. I don't have to break it or I don't have to digest it. I can put it into a certain bottle and I can count, I will get the result. After the counting, I can give back to you. So now we will understand how this works and what is the main methods that we use and how you can also basically basics of these detectors. Okay, so in this lab, look around and see if you can identify the types of detectors. Can you please look around and see what are the detectors available over here? No. How many?
DNA, 1 HPG.
Wrong. It's the other way around. So we basically have 3 HPG and 1 sodium iodide. So the easiest way to identify a HPG is that HPG will always have a liquid nitrogen cylinder with it. At most of the cases, unless it is very advanced HPGs have electronic cooling, but again it will have something below. Sodium iodide will not have anything. So yeah, so this is HPG, one of the HPGs. There is one more HPG over there, there is one more HPG over there, and this is a sodium iodide detector. So that HPG is around 22 years old. That one is again, it was procured in the year 2008. This one is the latest procured almost 10 years back. It's 2015. Okay, so now let us see why gamma spectroscopy, gamma spectrometry. So as you have learnt in the classes, so when an alpha and beta decay happens, the daughter product, daughter radionuclide might not always go into the ground state energy and might be in the excited state, and from there it will emit a gamma or X-ray or any auger electrons to come to the ground state. That gamma is what we are identifying here. So not all, when this process happens, not all the like let us say if there are 100 atoms, for example, if I take the case of cesium, not all the 100 cesium will give this 661 the gamma peak. So 5% will go directly, 95% will go to the excited state. So of that 95%, only of the 100, total 100, only 85.4% of the particles will give you the cesium peak, the 661 peak. That is it will emit that 661.6 keV of gamma. So this is what we spoke about the yield in the earlier classes. So now, please move back, I will show this detector. So this is our HPG. So let me start with whatever is the physical appearance of this HPG. So basically, you can see that there is a big shielding over here. So this shielding kept in order to reduce the background noises. For example, you are going to learn, unlike our popular assumption that radiation is not available everywhere. Radiation is like radionuclides are available in the air we breathe, in the water we drink, in the soil we live on. So these radionuclides, maybe from cosmogenical sources, from terrestrial sources, will interact with the detector if I keep it open, right? So I'll have to reduce the interaction of this radionuclides that is not required in the counting process. So we have kept a 10 centimeter thick lead shielding over here. So you can see how thick it is. So this thick lead shielding, and then you have the detector under this. So this tissue paper is kept to remove any kind of particles that fall into it. So you can see that that is the, yes, we keep the sample on top of this one. This is again another protective cover. So the main thing is that there should not be any kind of dust particle falling into it. So we will have to always keep the tissue, and below that there is the detector. Okay, is it done? Yeah. So now, so that is why we keep it always closed. So because once the, suppose what will happen if there is some kind of dust particle inside? Yes, so background increases. So if background increases, there is another parameter that increases, that I'll tell you later. So from that detector, so you have seen the detector. This detector, HPGE, the name says that high purity germanium. So germanium is a semiconductor material. So how do you convert this semiconductor material into a detector? So how does a semiconductor is nothing but a PN junction diode. That is what we are having here. So we reverse bias it. Okay. So when you reverse bias it, what happens? There is a large area of depletion region that is created. So when your sample has some radiation sources, radionuclides, it falls on this depletion region, there is an electron hole pair is generated. Okay. So that means a current is generated. So that current is what we get here as peaks. I will tell how it happens. Now, can you tell me the rationale behind keeping a liquid nitrogen, this detector immersed in liquid nitrogen? With the information you have got now. Why should I maintain the temperature? No. Yes, sir. Ah, yes.
Temperature increases with the pulse noise.
Yes. So semiconductor is very sensitive to temperature changes. So if I keep it in room temperature, lot of thermal electrons can be generated. That will contribute to your signal. Then you cannot distinguish between what is your signal, what is your noise. Or so that is why we have to maintain a constant temperature. That too we have to, so semiconductor acts as a semiconductor, we know that it acts like a conductor in a room temperature, and it works as an insulator at 0 degree Kelvin. Yeah, so that is why we keep it in a liquid nitrogen. Liquid nitrogen temperature is around minus 170 degrees Celsius, so 169 to be preferred. So to be precise, so we use liquid nitrogen in order to suppress these all thermal neutrons, thermal electrons.
Is it circulating inside?
No, sir. That I will tell you. I will tell you how. So now the signal is generated. That signal is transferred through the cables to this box over here. So this is called as an amplifier. I will explain in detail over there. So amplifier plus a multi-channel analyzer. Okay, so amplification happens here. Now think about it. The current generated over is very small, and while transferring from there to here using cables, wouldn't be there any noise? There will be lots of noise. So I have to remove this noise. What should I do? Any idea?
You have to increase the
Signal pulse and remove the noise. So for that we add a preamplifier embedded in the detector. Okay. So there is a preamplifier over there. So that preamplifier amplifies the signal, and then that is transferred to this main amplifier. Okay. From there it goes to multi-channel analyzer. So what is this multi-channel analyzer? So think about, so it has an electronic circuit where there is a lot of spaces. Let us assume that there are so many boxes, and each box I will assume that for example one box I will say that this box gives should, if any radiation of 0 to 1 keV comes, it should go to this box, box number 1. Second box is from 2 to 1 to 2 keV. Third box is 3 to 2 to 3 keV, so on. So each box will be assigned specific energy. So whenever the signal, so amplified signal comes, according to its energy, it will put it into these boxes. There are no boxes inside, but I'm just saying. So it will, there are lots of boxes. Okay. Now that boxes or that spectrum is viewed over here. Okay. So for example, now I'll show you from the beginning. So this is our starting peak. So this is 326 channel. So it corresponds to 32.6 kilo electron volt. So next channel is 327, which corresponds to 32.7 kilo electron volt. So my one channel is 0.1 kilo electron volt. So every 0.1, if there is an energy difference between 0.1, still it can resolute and put into different channels. Okay. So now how do we, how a peak is generated? How this peak comes? Okay. So let us go to the first peak over here. So I'll identify what the peak is. So we will put a cursor on the top of this peak. So peak value is peak channel number is 46.8 kilo electron volt. Actually this should have been, there will be slight shift here and there. This peak is 46.5 kilo electron volt, which is of lead 210. Okay.
The binding energy, sir?
What binding energy?
Sorry. Before getting that peak, some other peaks are there. That means
see this peak before the whatever the lower peaks, lower peaks is not observed in this HPG. So high purity germanium detector, the see it depends upon your carbon window. So the window. So we have a carbon window which can start detecting from 30 kilo electron volt. Okay, and then if you have an aluminum window, I think sir it is 100 keV. Aluminum, yeah, something like that. And then there is another composite window, again it will give some other energy. So we have the best one, that is carbon window, which will start counting from 30 kilo electron volt. So anything below that you cannot detect by HPG, at least by this HPG. I don't know if there is any other HPG that can detect lower than that. Okay. Now, and again that those from 30 to 46.5, this sample, this is an uranium source. It does not have that peak. So there is no uranium signal, radionuclide daughter of uranium that is giving a peak between 30 to 46.5. 46.5 is the first peak, that is lead 210. Okay. Now, as I said, if I come to the one end of the peak, see, I'll zoom this area, single peak, we will zoom it. Okay, this I will take as my start of the peak. Will you agree? This point, this point, this point, no? Then which one will you take? Slightly further, over here. Okay, you can take that. Now, wait, you said over here, right? Now this one is the starting of the peak, right? Okay, I will take that one. So this is the start of my peak and this one is the end of my peak. Will you agree? Little bit this side. Okay. Over here. Will you agree? Okay. Now, see this channel over here, this channel 45 point, so no, not that. Yeah, 45.6. It has counts of 2368. Okay, this channel, this one channel. The next channel over here has counts of 2463. So, so on, so on, so on, so on, so on, so on. You have 9000, 10,000, again 9000. 46.8 has a peak energy of 10,250. Now, for me to identify how much activity of lead-210 is present, I want the whole count of this peak. Okay. So, that is given, I have marked two areas. This is my starting marker, this is my left marker, this is my right marker, and I'll see that total counts under this area is 78,378. That means total of this whole area contains 78,378 counts.
Central?
Centroid is that one, 46.8. Yeah. So that is the lead to 10 counts in this sample. Now what is my counting time? Counting time is 60,000 seconds. So counts per second is calculated by
Parameter is same for all.
what
Like
parameter?
60,000.
No, it depends. I can set it like 30,000. If I want, if the activity is high, I can set 10,000, 5,000, even 1,000, 100 seconds.
You set instead of 60, 10,000.
You might not get this big peak.
Big peak.
You might get
Is there any difference with respect to that the centroid?
no.
It might be same.
It might be the same, but you have to get a proper peak. So, for example, I'll show you. So this is counted for 40,000. Show me a peak.
Less time, less count.
There is no peak. This count does not have any peak. So this is a low active sample. This does not have lead to 10 peak over there. This does not have any peak other than what? See, you have only one peak over here. This is 511.2. That is not a peak from the sample. This is a annihilation. Annihilation peak. So then you have one peak over, the only peak over here is K40 peak. Okay, so if I start, if I count this sample for maybe, I can experiment, I can start counting this for 1 lakh seconds, 1,50,000 seconds. Even if there is small activity, it might get detected. So counting, radiation counting depends upon time, distance and shielding. So you can increase the time, you can reduce the shielding in the sense, shielding between the detector and the sample, and distance. So distance, it is 0. I have not kept any distance between the, I cannot reduce the distance, I cannot reduce the shielding because there is no shielding. So I can only increase the time of counting to get the maximum counts. Okay. So that's about these things. And okay, so once I get the total counts, so total counts I have got over there 76,000 something, I divide it by the time, counting time, to get counts per second, CPS. Yeah.
If we change that time, you are saying that 60,000 seconds. What about the HV?
It will not change. It is set.
Set.
Yeah.
Okay. If we what is the HV for present?
4.5 kilo electron volt. 4.5 kilovolt.
Kilovolt.
Yeah.
Okay. Energy level time only change ಆಗ್ತಲ್ಲ ನಾನು applied voltage ಏನು changes
ಏನು ಮಾಡಲ್ಲ.
applied voltage ಎಲ್ಲ fixed.
It is all fixed. There is no other parameter that we can change. Only parameter I can change is time.
Only time.
Yes, I cannot change the voltage. If I change the voltage, the spectrum shifts.
Okay, spectrum will be shifted.
Yeah.
Spectrum will be shifted. Either that is lower side or higher peaks.
Yeah.
According to that peaks, you are setting your timing.
No. Once you are set your high voltage, you will not change it at all. So if you change your high voltage, your spectrum gets shifted. So you don't want your spectrum to shifted. Your energy calibration will go wrong. So for example, if this peak comes at over here, let us, then I cannot say this is lead. This lead 210 peak, if it comes here, I can say that it is uranium. So I don't want this peak to shifted. So once I set the high voltage, I will never change it.
High voltage is the operating voltage given to the detector. Okay. So each detector will have a designed high voltage, operating voltage. Once it is set, it is done. You are not going to change its daily. So, for example, if I start the switch on the detector today, I set the detector voltage at 4,500 volts today. That's it. You are not playing with that again. Then you are only collecting the data with the detector. You daily change the sample, acquire the spectrum.
When it switch off, again we can look.
When you switch off,
again we can
reduce it to 0, and then switch off. And then you, after 2 days, you switch on. You again set it to 4,500.
Okay. So once we got the counts, they count the activity, as I said, using the formula CPS into 100 by the yield of the peak into 100 by the efficiency. So now we have another factor over here, which is efficiency. So we have to calculate efficiency. How do we do that?
That that we can
Okay.
is about the calculation method. We there do that.
Okay.
Now today you limit your explanation. What is the system? Gamma spectrum.
Okay.
There is a detector. Detector is maintained liquid nitrogen, and there is a spectrum analysis,
Yes.
hardware and software.
Yes, sir. That much is done. Yeah. So then.
And then about the procedure, how to count the sample, how to take the counts under ROE, and how to determine the efficiency, how to subtract the background, and how to calculate the activity, we will demonstrate tomorrow.
Okay, sir. Yeah. So this is about HPG. Yeah. So this is about HPG. Any doubt about HPG now? Okay. So yeah, then we can go to the sodium iodide detector. So the same spectrum, whatever I have, same sample which I have kept over there, I am showing it here. But before going to the spectrum, we will just I'll just explain about the system. So there you had a semiconductor detector, right? Semiconductor detector, we reverse biased it and all those things I have explained. So can you give a little bit back? Yeah. So this system is a scintillation detector. Okay, this is a sodium iodide crystal which is doped with thallium. Okay, thallium doped sodium iodide crystal which is kept inside this. This is a well type detector. Okay. So now what is the difference between this and that? Is that, yes sir?
After you finish this batch, let them go for tea.
Okay.
We give them 10-15 minutes gap.
Okay, sir.
For a break for tea.
Then
we'll resume.
okay, sir. Yeah. So now the main difference between this and that is that here, after the sample will when the radiation falls on this crystal, scintillation is produced. That sparks of light. Yeah, not spark, like scintillations of light. Scintillations of light is produced. This one, once this is directly the intensity of the scintillation is directly proportional to the incident of energy. Now one scintillation photon, we have to convert it into electron for counting to get as a signal. So that is converted into electron using a no, before that, no, before that, photosensitive. No, before photomultiplier tube there is something. Cathode. So there is a photocathode that converts this photon into electron. That electron, that is single electron, is multiplied using photomultiplier tubes. One is converted into 2, 2 is to 4, 4 into 8, so much, 2 to the power n times we multiply it, and then the same system continues. You have, see, I told you the high voltage power supply, this is the amplifier, and then you have a multi-channel analyzer. So first high voltage will go to the detector, from there it comes to the amplifier, pre-amplifier is already inside, then amplifier, from amplifier it goes to a multi-channel analyzer. So then the spectrum is obtained. Same thing. Now, this is GIAN 2000. Okay. Now, what is the difference between this and that? Sodium iodide. Yes, resolution is poor. Their resolution is good, which is having higher efficiency. This HB sodium iodide is having higher efficiency. Any other difference can you see between that spectrum and this spectrum? That is what resolution is. Resolution is. Anything else? Look at that peak. Look at this peak. See something is different. No, that is zoomed in. That is not. There is some difference. This is basically the same peak, same sample. Uranium I have kept over there. Uranium I have kept over here. I have counted. That's it.
Energy level overlapping.
That is there. Anything else? Anything else that you can look at the peak? So can you see this? There is a slope over here. So this is actually Compton effect. Okay. So this peak, their Compton correction will be done by the Compton correction. I'll explain. Wait. So Compton correction is done by the system itself. The total count you get is Compton corrected count. Here, however, this peak, whatever, this is thallium 171. So this is the bismuth 214 peak. This peak energy it will contribute. This will contribute some activity to the peak before it. So led to so K40 will be affected by the presence of bismuth 214 or thallium 208. So we have to correct it. So Compton correction, there is some formula that we'll learn later. So that is what there is. Compton corrected peak. This is not corrected peak. That's it. I hope.
How many channels do you have?
This system is 16K, 16,000. That system is 32,000. So that is 16,000. That is 60,000. But here we have limited it to 1,000.
We use 8.
Yeah. So this 16,000 we are, for sodium iodide we have limited to 1,000 channels because resolution is anywhere poor. So it's better to have it at 1,000 channels. So, but 32K will give you a much better resolution. Yeah. Yes.
So the size of this size of
That is 3 by 3. 3 by 3 crystal sodium. Okay, so this is a well type. There is different types of detectors comes. You have coaxial, you have planar. So our HPGs are coaxial detectors, and this one is a well type detector. So the advantage of well type detector is it can detect 360 degree. Okay, you can keep a sample inside it.
Okay. So if we increase the size of the detector, can you differentiate between the?
We cannot, like, I cannot increase the size of the detector
No,
as per.
you cannot
Yeah,
increase it.
but
If
yeah,
you use a
I'll tell
4
you.
by 4
Yeah,
by 4 or 5 by 5.
then efficiency will increase.
Efficiency will increase.
Right?
In our laboratory, we have 4 by 4 NITI.
Okay. So efficiency would be good, I assume. I'm not wrong. Am I wrong? No, he said that what if we use a bigger detector instead of 3 by 3? If I use a 4 by 4 detector,
Whether efficiency will change? Same.
it will increase, right? Counting area will increase, so more surface area for detection, I guess.
I have one question. How often do you measure the background?
Sir, every 15 days. So yeah, every 15 days.
How long is the background?
So for HPG we measure it for 60,000 seconds, or sometimes even 82,000 seconds. That is basically 1 day. This one 10,000 seconds, because I count the sample for 10,000 seconds. So background and sample I keep it for the same time. It is all from IAEA. Thorium 232. Geometry, various geometry. We have all most of like different geometries. For example, you give me a sample in a box, like a square box, then we have square geometry. We but mainly use this kind of geometry, wide mouth. This geometry we use for because this we have thorium and uranium standards in this. We also have no, it is not available now. RGA is not available.
I am writing same only. It look like white color.
Yeah, it is white color.
White color only. So PRC certificate. Uram thora potassium also.
Which one?
PRC.
Okay.
Recently certificate for the
Okay.
standard. IRMK is like
Okay.
This is circle.
Okay.
Circle that some minerals contain the 300 ppm uranium.
Okay.
So there is a circle is used for the standard for the uranium.
Okay.
And the monoxide contain around
that is used
300
yeah.
thorium. So this is monoxide is used for the
thorium.
Thorium.
Okay.
So you will submit the
BRC.
certificate for
okay.
Distribution to the all HPV.
Okay. But this one we procured from IAEA long back. So we have geometries, various other geometries also. We have bottle geometry for water samples. We have this small geometry for well type samples. We have various geometries.
From IAEA, no problem. But in
calibration, no. Once you
I am taking about this calibration of standard.
Calibration of standard is if that is difficult, yeah. Yeah. So calibration once.
Calibration, no problem.
Yeah, standard calibration.
Maintenance AMC.
No, standard calibration you can do one simple thing is that you can keep the same. You have a IAEA standard or any certified standard. You measure the efficiency. Then you keep your sample maybe 10, 15 times and calculate the calculation.
No. You are using one standard. You are preparing. You are using the one standard.
Yeah.
So other people are not accepting.
That is what.
So that is a problem. So
yeah.
Standard is universally
accepted. Yes.
Everyone.
Yes. Okay, then any questions?
No,
yeah. So I think we can take a break for tea. This is, I think, 2015, I guess, yeah, 2015. Yeah.
All this latest
That is 2005. Not 2003.
German. Sodium iodide.
This is also from Canberra.
Canberra.
Oh,
2015
yes, yes. Everything is from Canberra. Okay. Yes, I think we can take a break.
Okay.
Thank you.
Thank you.
Thank you.
Thank you. Yeah. So in our laboratory we have 4x4 centimeter.
Okay.
So they will calculate any individual purification.
Yes, you can only do in sodium iodide. You can only do sodium iodide. You can't do anything.
So my topic is depth profile soil samples.
Okay.
So in that only I calculate activity only. Is there any parameters you can calculate?
What?
Apart from the activity.
We can only calculate activity. Apart from that, I don't think.
So the different opinions are coming like that. Why are we only activity only? If try to other parameters. What is the applications in the depth? I'm choosing depth means there is no work at all. So it is an initial basic data. Chai given problem like decay region. So many people are asking, why are you taking the depth? Is there any applications?
I am not.
Any concerns? Where is the
No, I think I don't know what else you are looking for, but HPG is
my
only.
coming here. I get
When we take a break.
one or two applications.
Yeah. After tea.
Yeah. At least I get one or two applications.
Yeah, we can ask.
ನಾಳೆ ನಾಳೆ ಅದೊಂದು ಶಾರ್ಟ್ ಇಲ್ಲ ಅಂತಿಲ್ಲ.
This one. Okay. This one
Next
is for nitrogen.
ಇದು ಮುಗಿದ ನಂತರ ಮೇಲೆ
So we parts
ಮೇಲೆ ತಂದ
nitrogen is not one. It is all this already used dry food. It will not put it for engagement. Evaporated and evaporated nitrogen will purge inside. Purge inside to remove any kind of other, like let us say radon, the air particles. So nitrogen to remove extra to get better there. So your other question was how to move. Yeah, how to transfer. So this is our cylinder. These are our cylinders. Yeah. Right. This is the transfer pump. Okay. We put it. You take that tube. That tube. We put it inside this inlet. And that is all. So we pump that. Then this is removed that time. During the filling. Yes.
That maintains the temperature to 40.
Liquid nitrogen.
Same temperature.
Yeah. And no, this one vapor. That is not for temperature. It's a vapor. It's a nitrogen. It's like pure nitrogen vapor. So that we purge inside this chamber. So if there is any kind of like, let us say,
the only you are transferring gas.
Gas.
Then why not a nitrogen?
No, you are not. You are confusing. Detector is dipped inside nitrogen. Detector is cooled by liquid nitrogen.
Inside.
Detector is over here. This is cooled by, I think, this inside. There is some kind of pipe, this connection which cools the detector to liquid nitrogen temperature to reduce that background. Okay. This is extra gas from the liquid that we purchase. Yes.
The two purpose.
Yes. So, for example, you can see here, we don't have that purging. Here there is no purging. This is old detector. We don't have purging. We just have the liquid nitrogen.
How much time is required after keeping a sample to purge the sample?
No delay. I hope I solved your doubt.
Earlier they had, but they are going to retire. So somebody has to know after that. So it's better to do it.
ಕೇಬಲ್ ಒಂದು ಇಳಿಸಿದ್ರೆ ಕೊಡಿ ಕೇಬಲ್ ತಪ್ಪಿಸಿ ಆ ಕಡೆ ಅಲ್ಲ ಈಚೆಯಿಂದ ತಪ್ಪಿಸಿ ಹೊರಗೆ ಹಾಕಿದ್ರೆ ಎಳಿಬೋದಾ? ಅಲ್ಲ ಆ ಕಡೆಯಿಂದ ಎಳಿದ್ರೆ ಆಯ್ತಲ್ಲ, ಒಳಗಿಂದ ಎಳಿಬೇಕು. ಆ ಕಡೆ ರೂಮಿಂದ ಹಾಗೆ ತಗೊಂಡೋದ್ರೆ ಇದು ಉದ್ದ ಲೆಂತ್ ಉದ್ದ ಉಂಟು ಇಲ್ಲ ತುಂಬಾ ಉದ್ದ ಇಲ್ಲ ಅಲ್ಲ ಇದೆ ಅಲ್ಲ.